Is deep space travel possible? This question has fascinated scientists, dreamers, and explorers for generations. As our understanding of the universe grows, the idea of humans venturing far beyond our solar system feels both thrilling and daunting. In this video, we'll explore the challenges, technologies, and possibilities surrounding deep space travel. Space may seem closer than ever with missions to Mars and beyond already on the horizon. But deep space, the vast expanse beyond our solar system, is another story entirely. What would it take for us to travel those unimaginable distances? What hurdles stand in our way, and how can we overcome them? Our current space exploration technology has taken us far, but reaching other stars requires advancements we can hardly imagine. The spacecraft we've sent beyond our solar system, like Voyager 1 and 2, took decades just to leave the sun's influence. For human travelers, we'll need something much faster and much more reliable. The biggest obstacle we face in deep space travel is distance. Space is vast beyond comprehension, and even our fastest spacecraft would take tens of thousands of years to reach the closest stars. To make deep space travel possible, we must dramatically increase our speed, potentially even break the laws of physics as we currently understand them. Propulsion systems are at the heart of any space travel conversation. Today's rockets are powerful, but chemical propulsion isn't enough for interstellar journeys. We'll need to develop new technologies, from nuclear propulsion to theoretical concepts like antimatter drives, to take us beyond the solar system. Another major challenge is survival. Space is an unforgiving environment, and the further we go, the more hostile it becomes. Radiation, lack of gravity, and long periods of isolation pose serious threats to human health. We'll need to develop advanced life support systems to keep travelers safe on journeys that could last decades or even centuries. Communication is another hurdle. As we travel further from Earth, the time it takes for signals to travel back and forth increases. This delay could be measured in minutes, hours, or even years. How will future astronauts stay connected with mission control and with Earth itself? Energy is a crucial factor too. Solar power works well within our solar system, but deep space travel may require more reliable sources of energy. Nuclear power, or even harvesting energy from the cosmos, could become key to sustaining long-term missions. What about the destinations? Deep space is more than empty voids. There are distant planets, potentially habitable exoplanets, and mysterious regions of space waiting to be explored. But how do we choose where to go first? And what might we find when we get there? Ultimately, the possibility of deep space travel pushes the limits of human imagination, technology, and willpower. The dream of exploring the stars is alive, but the road ahead is long and uncertain. Let's dive deeper into the technologies and breakthroughs needed to make this dream a reality. Rockets have been the backbone of space exploration since the beginning. They work by expelling mass at high speeds, generating the thrust needed to escape Earth's gravity. But for deep space travel, traditional rocket technology has significant limitations. Chemical rockets are powerful but inefficient for the immense distances involved in deep space. Their fuel requirements grow exponentially with the size of the mission. This creates a challenge. How do we carry enough fuel to go further without making the spacecraft too heavy to launch? Nuclear propulsion offers a potential solution. By harnessing the energy from nuclear reactions, spacecraft could travel faster and more efficiently than chemical rockets. This technology has been theorized for decades, but there are still many hurdles to overcome before it can be used for human missions. Electric propulsion systems, like ion thrusters, are another promising option. These systems use electricity to ionize gas and create thrust, allowing for much longer, sustained acceleration. While they provide less initial power, they could gradually build speed to reach incredible velocities over time. Solar sails present a completely different approach to propulsion. By capturing the momentum of photons from the sun, these large reflective sails could push spacecraft through space. This method requires no fuel, but it is dependent on proximity to a star and takes time to build speed. Antimatter propulsion is one of the most exciting and speculative ideas in propulsion technology. When antimatter and matter collide, they release vast amounts of energy. Harnessing this energy could, in theory, allow spacecraft to achieve near-light speeds. However, antimatter propulsion remains theoretical. Producing and storing antimatter in the quantities needed for space travel is currently beyond our technological capabilities. Even if this becomes possible, the safety concerns of handling such a volatile substance are immense. Fusion propulsion could be the key to unlocking deep space travel. By mimicking the process that powers stars, fusion engines could provide a continuous and powerful source of energy. Unlike nuclear fission, fusion is cleaner and has the potential to provide far greater efficiency. Despite its potential, fusion propulsion is still in the experimental stage. Scientists are working on ways to control fusion reactions and convert the energy into usable thrust. If successful, this could revolutionize space travel and bring deep space destinations within reach. One challenge that remains for all propulsion systems is how to sustain power over the long distances of deep space. Spacecraft will need to operate for years, if not decades, without refueling. Developing propulsion systems that can provide reliable, long-term thrust is essential. The future of propulsion might also involve hybrid systems. Combining different propulsion methods could offer flexibility, allowing spacecraft to use chemical rockets to escape Earth's gravity, and then switch to more efficient systems for deep space travel. This strategy could maximize the strengths of multiple technologies. As we explore these different propulsion options, it's clear that no single solution will be the answer. The next generation of deep space travel will depend on a combination of advanced technology, new scientific breakthroughs, and creative engineering. Each propulsion system offers possibilities but also presents its own unique challenges. When we think about spacecraft design, durability is one of the most critical factors. Deep space is an incredibly harsh environment, exposing spacecraft to radiation, extreme temperatures, and micrometeoroids. Engineers must create vessels that can withstand these conditions for extended periods without breaking down. Materials used in spacecraft construction need to be incredibly strong yet lightweight. Traditional metals like aluminum are often used, but new materials such as carbon composites are becoming increasingly common. These advanced materials offer greater durability while keeping the spacecraft's weight as low as possible. Spacecraft must also endure the intense vibration and pressure of launch. During takeoff, the structural integrity of the craft is tested to its limits. If even a small flaw is present, it could be catastrophic once the vehicle is in orbit. Thermal protection is another key aspect of spacecraft design. In space, temperatures can vary wildly between the scorching heat of the sun and the freezing cold of the shadows. Spacecraft must be insulated to protect both its systems and its crew from these extreme conditions. Radiation is one of the biggest threats to both the spacecraft and the humans inside it. Outside the protective shield of Earth's magnetosphere, cosmic radiation can damage electronic systems and pose serious health risks to astronauts. Engineers must design radiation shields that can block or deflect these harmful particles. Micrometeoroids are small, high-speed particles that can cause significant damage to spacecraft over time. Even tiny impacts can puncture the hull or damage sensitive instruments. Spacecraft require strong outer shells and, in some cases, layered shielding to absorb these impacts. Redundancy in spacecraft systems is crucial for long-term durability. Every critical system, from navigation to life support, must have a backup in case of failure. This redundancy ensures that if one component breaks down, the mission can continue without jeopardizing the crew or the spacecraft. The interior design of the spacecraft must also be functional for long-term missions. Space is limited, so every inch must be used efficiently, providing both operational space and a livable environment for the crew. Durability isn't just about the exterior, it's about creating an interior that can sustain life for years. Maintenance in deep space poses unique challenges. In the event of a malfunction, astronauts may need to repair or replace components in zero gravity. Spacecraft must be designed with this in mind, making it possible for the crew to access and fix systems with limited tools and resources. Designing spacecraft for long journeys means thinking about future-proofing. Missions that last decades might encounter new problems we can't yet foresee. Engineers must build spacecraft that can be adapted or repaired remotely as new technology or challenges arise during the mission. Longevity is key. A spacecraft bound for deep space must operate for many years, far beyond the typical lifespan of current space vehicles. Every component must be rigorously tested to ensure it can withstand the extreme conditions of space for the long haul. As spacecraft design evolves, future missions will demand increasingly sophisticated solutions. Durability in deep space travel isn't just about surviving. It's about thriving in one of the most hostile environments known to humanity. Engineers are pushing the limits of what's possible, creating spacecraft that can carry us further than we've ever gone before. As spacecraft venture farther from Earth, communication becomes increasingly challenging. The vast distances involved mean that signals take longer to travel back and forth. This delay can range from minutes to hours, depending on how far the spacecraft is from our planet. One of the primary challenges in deep space communication is signal strength. As the distance between Earth and the spacecraft increases, the signal weakens. Powerful antennas and advanced signal processing technologies are required to send and receive clear messages across such vast distances. Deep space networks like NASA's DSN are crucial for maintaining communication with distant spacecraft. These networks consist of large radio antennas strategically placed around the globe. By working together, they can ensure continuous contact with spacecraft as Earth rotates. Latency is another issue that becomes significant in deep space missions. When signals take minutes or hours to reach their destination, real-time communication isn't possible. This delay requires spacecraft to be equipped with more autonomous systems that can make decisions without waiting for instructions from Earth. The farther we travel into space, the more data we need to transmit back to Earth. High-bandwidth communication systems are essential to send scientific data, images, and other information. However, the farther a spacecraft is, the more difficult it becomes to transmit large amounts of data quickly. To overcome this, scientists are exploring new methods of communication, such as lasers. Laser-based communication can potentially transmit data much faster than traditional radio waves. However, it requires precise targeting and is still being developed for use in deep space. Spacecraft must also be equipped to handle communication blackouts. Certain parts of their journey, such as passing behind planets or through areas with high radiation, can interrupt the signal. During these periods, the spacecraft must operate independently until communication can be re-established. Another factor to consider is the potential for interference from cosmic radiation and other celestial phenomena. These can disrupt communication signals, making it difficult to maintain a consistent link with the spacecraft. Engineers must design systems that can filter out noise and maintain clarity in these conditions. Onboard systems also need to manage communication resources efficiently. Limited power supplies mean that communication equipment must be used sparingly and strategically. This requires spacecraft to balance energy consumption between maintaining contact with Earth and powering other critical systems. As missions extend further, communication with multiple spacecraft at once becomes more complex. Coordinating signals between Earth orbiters and landers requires precise timing and organization. This networked communication approach ensures that no data is lost and that mission objectives are met. Future communication systems might rely on relay stations positioned throughout the solar system. These stations could act as intermediaries, boosting signals between Earth and distant spacecraft. Such a system would make long-range communication more reliable and faster. Ultimately, communication is the lifeline between Earth and deep space explorers. Without reliable and efficient communication systems, long-duration missions would be far riskier. Scientists and engineers continue to innovate, ensuring that as we push deeper into space, we stay connected every step of the way. For long-term space travel, life support systems are essential to keeping astronauts alive and healthy. These systems must provide air, water, and food, while also regulating temperature and removing waste. In the vast emptiness of space, there's no room for error. Oxygen generation is one of the most critical functions of a life support system. Without a constant supply of breathable air, astronauts would quickly be in danger. Systems like the ones used on the International Space Station split water molecules to create oxygen, but long journeys will require even more efficient methods. Water recycling is another crucial aspect. Spacecraft can't carry enough water for extended missions, so they must recycle as much as possible. Advanced filtration systems clean wastewater, including sweat and even urine, to make it drinkable again. Temperature control in space is a constant challenge. Spacecraft are exposed to extreme temperature fluctuations, from the intense heat of direct sunlight to the freezing cold of deep space. Life support systems must maintain a stable, habitable temperature inside the spacecraft at all times. Waste management is equally important. On long missions, waste can't just be discarded. Instead, it must be processed and recycled where possible. Efficient systems for handling both human waste and general waste products are vital for maintaining a healthy living environment. Another challenge is providing adequate nutrition. Growing food in space might be a necessity for long-term missions, as carrying enough supplies isn't feasible. Experiments with hydroponics and other methods are underway to develop sustainable food sources for future space travelers. Protecting astronauts from radiation is a top priority for life support systems. Beyond Earth's atmosphere, exposure to cosmic rays and solar radiation increases dramatically. Shielding and advanced protective measures must be integrated into the spacecraft to minimize health risks. Long-term isolation also presents psychological challenges. Life support systems may need to incorporate elements that address mental health, such as lighting systems that simulate Earth's day-night cycle, or entertainment options to help astronauts cope with isolation. In space, maintaining the balance of gases is critical. Carbon dioxide must be removed from the air to prevent poisoning, and other gases like nitrogen must be regulated. This delicate balance is managed by complex systems designed to mimic Earth's atmosphere. Powering life support systems over extended periods is another obstacle. These systems require continuous energy, which must be carefully managed alongside the spacecraft's other needs. Efficient energy use and reliable power sources are essential for long-duration missions. Backup systems are necessary in case of failure. Redundant systems ensure that if one life support function breaks down, another can take over. This is crucial for missions that venture far from Earth, where immediate help isn't an option. Life support systems for deep space travel must be highly automated. Astronauts can't spend all their time maintaining these systems, so they must be designed to run with minimal human intervention. Automation ensures that the crew can focus on their mission without constant worry about their basic needs. As we prepare for longer journeys into space, life support systems must evolve to become more resilient and efficient. These systems are the key to survival, enabling humans to live and work in the most extreme environment imaginable. Space agencies have been at the forefront of advancing space exploration technology for decades. Organizations like NASA, ESA, and Roscosmos have driven innovation, pushing the boundaries of what is possible in space travel. Their missions lay the groundwork for exploring deeper into space than ever before. NASA continues to lead with programs like Artemis, aiming to return humans to the Moon and eventually land them on Mars. These missions not only push human presence further into space, but also test technologies crucial for deep space travel. The lessons learned from these missions will shape the future of exploration. The European Space Agency plays a vital role in international collaboration. ESA works alongside other agencies to develop key technologies, from spacecraft design to propulsion systems. Their contributions to joint missions help foster a united approach to space exploration. Roscosmos, the Russian space agency, brings decades of experience to the table. Their expertise in launching and maintaining spacecraft is crucial, especially in manned space missions. They remain a key player in global efforts to advance space travel. China's space program has seen rapid growth in recent years. With ambitious plans for lunar exploration and space station development, China is emerging as a major force in space technology. Their long-term goal of sending humans to Mars puts them at the forefront of deep space exploration efforts. Private companies are transforming the space industry, accelerating the pace of innovation. SpaceX has revolutionized rocket technology with its reusable launch systems, drastically reducing the cost of getting to space. Their Starship program aims to enable long-duration space missions, including interplanetary travel. Blue Origin, founded by Jeff Bezos, is also making significant strides in space technology. With a focus on reusable rockets and lunar exploration, the company aims to create a future where millions of people live and work in space. Their vision aligns with long-term goals of deep space exploration. Boeing continues to be a key player, especially with its role in developing crewed spacecraft. The CST-100 Starliner is designed to transport astronauts to the International Space Station and beyond. Boeing's experience in aerospace engineering positions it as a major contributor to future deep space missions. Lockheed Martin is heavily involved in designing spacecraft for deep space exploration. Their work on the Orion spacecraft in partnership with NASA is critical for future missions to the Moon and Mars. Orion is built to withstand the harsh conditions of space, making it a key vehicle for long-term exploration. Smaller private companies are also entering the space race, bringing fresh ideas and innovative technologies. Companies like Rocket Lab are developing smaller, more efficient rockets, while others are exploring niche areas like asteroid mining and space tourism. These smaller players bring agility and creativity to the industry. Collaboration between space agencies and private companies is becoming more common. These partnerships leverage the strengths of both sectors, combining governmental experience with private sector innovation. Together, they are pushing the limits of space exploration faster than ever before. As space agencies and private companies continue to advance technology, the dream of deep space travel moves closer to reality. Each breakthrough, whether in propulsion, spacecraft design, or life support, brings us one step closer to exploring the distant corners of our universe. Chemical propulsion is the most widely used form of space travel today. It relies on burning fuel to create thrust, which pushes spacecraft into orbit and beyond. While it's effective for short distances, chemical propulsion has significant limitations when it comes to deep space travel. The principle behind chemical rockets is straightforward. A controlled explosion of fuel creates high-pressure gases, which are expelled through a nozzle to generate thrust. This method has been used since the earliest days of space exploration and remains the standard. However, chemical propulsion systems are extremely fuel-hungry. The amount of fuel required to escape Earth's gravity and travel long distances is enormous. This presents a challenge for deep space missions where carrying enough fuel becomes impractical. One of the biggest drawbacks of chemical propulsion is its efficiency. The specific impulse, or the amount of thrust produced per unit of fuel, is relatively low. This means that rockets must carry a large amount of fuel to achieve high speeds, adding significant weight to the spacecraft. Liquid fuel rockets are the most common form of chemical propulsion used today. They offer greater control and efficiency compared to solid rockets, making them ideal for missions requiring precise maneuvers. Liquid oxygen and hydrogen are often used as the propellant, providing powerful thrust. Solid rocket boosters are another form of chemical propulsion, often used in conjunction with liquid fuel engines. These boosters provide an extra burst of power during launch, but are not as efficient for longer missions. Once ignited, solid rockets can't be shut down or controlled, limiting their flexibility. Hybrid propulsion systems combine elements of both liquid and solid rockets. They use a solid fuel with a liquid oxidizer, offering more control than traditional solid rockets. While hybrids offer some advantages, they are still largely experimental compared to established chemical propulsion methods. Despite its limitations, chemical propulsion remains essential for launching spacecraft into orbit. It provides the necessary power to overcome Earth's gravity, allowing vehicles to reach space. Once in space, however, alternative propulsion methods are often considered for longer journeys. One way to improve chemical propulsion systems is by increasing their efficiency. Engineers are exploring new fuel combinations and engine designs to squeeze more performance out of these systems. These advancements could extend the range of chemical rockets, though they still face inherent limitations. Another challenge with chemical propulsion is the environmental impact. Rocket launches release significant amounts of carbon dioxide and other pollutants into the atmosphere. Developing cleaner fuels and more efficient engines could help reduce the environmental footprint of future space travel. While chemical propulsion may not be the solution for deep space travel, it remains a crucial part of space exploration. For now, it provides the raw power needed to get us off Earth and into orbit. The future of propulsion may lie in more advanced technologies, but chemical rockets will continue to play a role. As we look toward longer missions and further destinations, the need for more efficient propulsion systems becomes clear. Chemical propulsion has taken us to the Moon and will likely help us reach Mars, but the stars will require something far more advanced. Nuclear propulsion is one of the most promising alternatives to chemical rockets for deep space travel. It has the potential to provide far greater efficiency and speed, allowing spacecraft to cover vast distances in less time. By harnessing the power of nuclear reactions, we could unlock new possibilities for exploration. The two main types of nuclear propulsion are nuclear thermal propulsion and nuclear electric propulsion. In nuclear thermal propulsion, a nuclear reactor heats a propellant like hydrogen, which is then expelled to create thrust. This method offers much higher efficiency compared to chemical rockets. Nuclear electric propulsion, on the other hand, uses a nuclear reactor to generate electricity, which powers ion thrusters or other electric engines. While this method produces less immediate thrust, it can run continuously over long periods, gradually increasing the spacecraft's speed to impressive levels. One of the biggest advantages of nuclear propulsion is its efficiency. Nuclear reactions release millions of times more energy than chemical reactions, meaning that nuclear-powered spacecraft could carry less fuel and travel farther. This could significantly reduce the weight and cost of deep space missions. For missions to Mars or beyond, nuclear propulsion could cut travel time dramatically. Reducing the time astronauts spend in space would lower their exposure to radiation and other hazards, making deep space missions safer. Faster journeys also mean we could send more cargo and equipment for long-term exploration. However, nuclear propulsion comes with its own challenges. Developing a compact, reliable nuclear reactor for space travel is no small feat. Engineers must ensure that the reactor can operate safely in the extreme conditions of space without posing a risk to the crew or the environment. Another concern is radiation. Nuclear propulsion systems generate radiation that could be harmful to both astronauts and the spacecraft itself. Shielding the crew from this radiation, while keeping the spacecraft light and efficient, is a complex engineering problem that must be solved. Nuclear propulsion also raises political and regulatory issues. Launching a spacecraft with a nuclear reactor on board involves significant safety risks. Any accident during launch could lead to the release of radioactive material, which is a concern for both governments and the public. Despite these challenges, interest in nuclear propulsion is growing. NASA and other space agencies are actively researching nuclear thermal and electric propulsion systems, with plans to test these technologies in the coming decades. Private companies are also exploring nuclear propulsion as a way to reduce the cost and time of interplanetary travel. If nuclear propulsion becomes viable, it could revolutionize space travel. Missions that currently take years could be shortened to months, opening up new opportunities for exploration. The ability to send heavier payloads and travel farther would transform how we approach deep space missions. The long-term potential of nuclear propulsion extends beyond our solar system. With enough development, these systems could enable interstellar travel, pushing humanity to the stars. While this is still a distant goal, nuclear propulsion could be the first step toward making it a reality. As research continues, nuclear propulsion may become the key to unlocking faster, more efficient space exploration. It offers a glimpse of what's possible when we tap into the incredible power of the atom, bringing us closer to the dream of deep space travel. Ion thrusters are a revolutionary technology that could change how we approach space travel. Unlike traditional rockets that rely on chemical explosions, ion thrusters use electricity to accelerate ions, creating a gentle but continuous thrust. Over time, this slow, steady acceleration can push spacecraft to incredible speeds. One of the major benefits of ion propulsion is its efficiency. It uses far less fuel than chemical rockets, allowing spacecraft to carry lighter loads and travel further distances. This efficiency makes ion thrusters ideal for long-duration missions in deep space. The way ion thrusters work is quite different from traditional engines. They ionize a gas, usually xenon, by stripping away electrons, creating positively charged ions. These ions are then accelerated through an electric field and expelled from the engine, generating thrust. While ion thrusters produce much less thrust than chemical rockets, they make up for it with endurance. They can run for months or even years, gradually building up speed. This makes them perfect for missions that don't require quick bursts of power, but instead demand long-term, sustained propulsion. NASA has already tested ion thrusters on several missions, including the Dawn spacecraft, which used ion propulsion to visit 2 different asteroids. Dawn's mission was a proof of concept, showing that ion propulsion could be used to navigate between distant celestial bodies over extended periods. Ion thrusters also open the door to more precise maneuvering in space. The ability to adjust speed and direction slowly and accurately is crucial for missions that require close-up exploration of planets, moons, or asteroids. This precision allows for detailed scientific observations and complex mission profiles. However, ion thrusters require significant amounts of electrical power to operate. In the vacuum of space, generating this power often comes from solar panels, or, in some cases, nuclear reactors. This need for a consistent power source can limit the capabilities of ion thrusters on missions far from the Sun. Electric propulsion systems, including ion thrusters, are increasingly seen as the future of deep space exploration. Their ability to function over long durations with minimal fuel consumption is a game-changer for extended missions. These systems could one day carry humans and cargo to distant planets more efficiently than ever before. Another advantage of ion thrusters is their scalability. Smaller thrusters can be used for satellites and probes, while larger versions could power interplanetary missions. This versatility makes ion propulsion a flexible option for a wide range of space missions. While still in development, future iterations of electric propulsion could see even more efficient systems. Advancements in energy generation and ion acceleration could lead to faster and more powerful thrusters, reducing travel time for deep space missions. Despite their slower acceleration, ion thrusters are more than capable of reaching high speeds over time. Given enough distance, a spacecraft powered by ion propulsion could outpace traditional chemical rockets. This makes ion thrusters a strong contender for missions to the outer planets or even beyond the solar system. As research and development continue, ion thrusters and other electric propulsion systems are poised to become an essential part of our toolkit for exploring the cosmos. These technologies are laying the groundwork for a future where deep space travel becomes more efficient and more attainable than ever before. Solar sails represent one of the most innovative approaches to propulsion in space. Rather than relying on fuel or engines, solar sails harness the power of sunlight. By capturing the momentum of photons, they can propel a spacecraft forward, slowly but steadily. The concept behind solar sails is simple yet powerful. Photons, though massless, carry energy and momentum. When they strike a large reflective surface like a sail, they transfer a tiny amount of momentum, pushing the sail forward. Over time, this force accumulates, allowing the spacecraft to reach impressive speeds. One of the biggest advantages of solar sails is that they require no fuel. Once deployed, the sail continuously accelerates as long as it's in sunlight. This makes solar sails an ideal option for long-duration missions, where carrying large amounts of fuel would be impractical. Solar sails are incredibly lightweight, made from ultra-thin materials like mylar or captan. These materials are strong yet flexible, allowing the sails to stretch over vast areas. The larger the sail, the more sunlight it can capture, which translates to more thrust. While the initial acceleration from solar sails is slow, they can gradually build up speed over time. In the vacuum of space, where there's no resistance, a solar sail could theoretically reach speeds far greater than traditional propulsion systems if given enough time and space. Missions like Japan's Ikaros and the Planetary Society's Light Sail have already tested solar sails in space. These projects demonstrated that the technology works and could be used for future exploration. Light Sail's mission, in particular, proved that small spacecraft can use solar sails to adjust their orbits and travel across space. One of the challenges of solar sails is their dependence on sunlight. As a spacecraft moves farther from the sun, the intensity of sunlight decreases, reducing the sail's thrust. This makes solar sails less effective for deep space missions, unless alternative light sources like lasers are used. Laser-driven sails are a concept being explored to overcome this limitation. Powerful lasers based on Earth or in space could continuously beam light at the sail, allowing it to accelerate even in the darker regions of space. This technology could push solar sail missions beyond the solar system. Solar sails also require precise control. Maneuvering a spacecraft with a sail involves adjusting its angle to the sunlight, much like a sailor adjusts the sails of a ship to catch the wind. This control allows the spacecraft to change direction or adjust its speed over time. Despite their potential, solar sails are best suited for lightweight missions. The thrust they generate is too weak to propel large spacecraft, but for small probes or exploratory missions, they offer a low-cost and efficient propulsion method. Future designs could scale up, potentially allowing for larger payloads. The lack of moving parts also makes solar sails highly reliable. With fewer mechanical systems that could fail, solar sails are a durable option for long-term missions. This reliability makes them particularly attractive for missions that might last decades or more. Solar sails represent a leap forward in how we think about propulsion. By harnessing the natural forces of light, we could travel vast distances without the need for fuel, opening new possibilities for exploration and making the dream of deep space travel even more attainable. Antimatter propulsion is one of the most intriguing and potentially powerful concepts in space travel. Antimatter is the opposite of regular matter, and when the two meet, they annihilate each other in a burst of energy. This annihilation releases far more energy than any chemical or nuclear reaction, making it a compelling option for deep space propulsion. Theoretically, antimatter propulsion could allow spacecraft to reach speeds close to the speed of light. The energy released from matter-antimatter annihilation is incredibly efficient, meaning only a small amount of antimatter would be needed to generate enormous thrust. This could reduce travel time to distant planets or even other star systems. One of the main challenges with antimatter propulsion is producing enough antimatter. Currently, antimatter can only be created in minute quantities in particle accelerators. Scaling up production to power, a spacecraft would require massive advancements in technology. Another hurdle is storing antimatter safely. Antimatter cannot come into contact with regular matter, as even a tiny collision would release energy. Scientists are exploring ways to store antimatter using magnetic fields, keeping it suspended in a vacuum to prevent contact with the walls of its container. Despite these obstacles, antimatter propulsion holds tremendous potential. The sheer energy density of antimatter is unmatched, meaning spacecraft powered by it could carry much less fuel than traditional rockets. This would allow for larger payloads or much longer missions without the need to refuel. In addition to speed, antimatter propulsion could provide the power needed for advanced onboard systems. The energy produced could be used to power life support, communications, and scientific instruments on long-duration missions. This dual use of antimatter's energy makes it an even more attractive option. However, the production of antimatter is currently prohibitively expensive. It costs billions of dollars to create even a few milligrams of antimatter. Until new methods of production are developed, antimatter propulsion remains largely theoretical and far from practical application. There are also concerns about safety. The destructive potential of antimatter, if not properly contained, could lead to catastrophic accidents. Designing systems to safely handle and control antimatter would be a critical part of making this propulsion method viable. Despite these challenges, research into antimatter continues. Some scientists believe that with enough time and investment, the technology could become feasible within the next century. The promise of nearly limitless energy and fast, efficient space travel is too great to ignore. In the distant future, antimatter propulsion could open up the possibility of interstellar travel. Reaching neighboring star systems, which currently seem impossibly far, could become a reality. The immense speed and energy of antimatter propulsion could make humanity a truly interstellar species. If antimatter propulsion can be developed, it would represent a quantum leap in space exploration technology. The ability to reach distant planets and stars in a fraction of the time would revolutionize our approach to the cosmos. The dream of traveling to other stars might no longer be science fiction. Though it remains in the realm of theory today, antimatter propulsion represents the frontier of what might one day be possible. If we can harness this incredible power, it could change the way we explore the universe, bringing us closer to distant worlds than we ever imagined. A light year is a measure of distance, not time. It represents how far light can travel in 1 year, which is roughly 5.88 trillion miles. Light travels at a speed of about 186,000 miles per second, making the distances in space incomprehensibly vast. When we talk about light years, we're describing the immense scale of the universe. The nearest star system to us, Alpha Centauri, is about 4.37 light-years away. That means light from Alpha Centauri takes more than 4 years to reach Earth. This concept highlights the challenge of space exploration. Even at the speed of light, which is the fastest speed in the universe, traveling between stars would take years. For humans, who currently travel far slower, these distances stretch into thousands or even millions of years. When we observe objects in space, we are looking into the past. Because light takes time to travel, the light we see from distant stars and galaxies shows them as they were years, or even billions of years ago. In a way, telescopes are time machines, letting us see the history of the universe. Light years also help us understand the scale of galaxies. Our Milky Way galaxy is about 100,000 light years across. That means even light, traveling at its incredible speed, would take 100,000 years to move from one side of our galaxy to the other. Distances to other galaxies are even more staggering. The Andromeda galaxy, our closest large neighbor, is about 2.5 million light years away. This means the light we see from Andromeda left that galaxy 2.5 million years ago, long before modern humans existed on Earth. Understanding light years also changes how we think about time in the universe. Events that happen in distant galaxies may have occurred millions of years ago, but we're only seeing the light from them now. This delay in receiving information is one of the great challenges of studying the cosmos. The vastness of light years makes interstellar travel incredibly difficult with current technology. Even the fastest spacecraft we've built would take tens of thousands of years to travel just 1 light year. To reach other star systems in a human lifetime, we would need to develop propulsion systems that far exceed anything we have today. When scientists describe the universe in terms of light years, it underscores just how small and limited our perspective is. Our entire solar system is just a tiny speck in the vastness of the galaxy, which itself is just one of billions of galaxies in the universe. Light years are also a reminder of how far we have to go in understanding the cosmos. The distances are so vast that even with all our advances in technology, much of the universe remains beyond our reach. Exploring these distant places requires both patience and incredible technological breakthroughs. As we look toward the future, the concept of light years will continue to be a fundamental part of space exploration. Whether we're observing distant stars or planning missions to other solar systems, light years help us grasp the incredible scale of the universe and the challenges that lie ahead. One day, if we can develop the technology to travel faster than light, the limits imposed by light years might no longer apply. But for now, they serve as a constant reminder of the vastness of space and the great distances we must overcome to explore it. Current spacecraft speeds are impressive by human standards, but still fall far short of what's needed for interstellar travel. Most spacecraft today reach speeds of tens of thousands of miles per hour. While that's fast enough to explore our solar system, it's a fraction of the speed of light. For example, the Voyager 1 spacecraft, which is the fastest and farthest human-made object, travels at about 38,000 miles per hour. Even at that speed, it took Voyager over 40 years to leave the solar system, and it would take tens of thousands of years to reach the nearest star. Newer spacecraft, like NASA's Parker Solar Probe, are breaking speed records. The Parker Solar Probe is designed to study the Sun and will eventually reach speeds of up to 430,000 miles per hour as it slingshots around the Sun. While incredibly fast, even that speed would take thousands of years to reach another star. Chemical propulsion, which powers most of our current spacecraft, is effective for planetary exploration but not suited for the distances between stars. These systems can provide enough thrust to escape Earth's gravity and travel through the solar system. But deep space requires much more speed. Ion thrusters, like the ones used on the Dawn mission, can operate for much longer than chemical engines, allowing a spacecraft to gradually build up speed over time. Dawn reached speeds of up to 25,000 miles per hour, but even that is not enough for interstellar distances. Solar sails also offer a promising alternative for deep space missions. Although their acceleration is slow, over time, solar sails could push spacecraft to much higher speeds. Missions like LightSail are testing this technology, but it's still in the early stages. Nuclear propulsion has the potential to boost spacecraft speed significantly. Concepts like nuclear thermal propulsion could drastically reduce travel time to planets like Mars. However, these systems are still being developed and aren't yet ready for interstellar travel. Antimatter propulsion, while still theoretical, could one day push spacecraft to speeds that are a significant fraction of the speed of light. Such speeds would make interstellar travel possible within a human lifetime, but we are far from having the technology to achieve this. Even at our current fastest speeds, traveling beyond our solar system would take an impractically long time. To reach Alpha Centauri, the closest star system, would take over 80,000 years with today's technology. Clearly, new breakthroughs in propulsion are necessary for faster travel. It's not just about raw speed, but also about how long spacecraft can maintain that speed. Current spacecraft engines provide bursts of power, But deep space travel demands systems that can operate continuously for years or even decades, something we're only beginning to develop. In addition to propulsion, spacecraft must also be designed to handle the challenges of high-speed travel. At extreme speeds, even tiny particles of dust in space can cause significant damage. Future spacecraft will need enhanced shielding to survive the dangers of traveling faster than we currently do. As we continue to push the limits of spacecraft speed, we'll need to balance efficiency, safety, and sustainability. Each new mission brings us closer to understanding how to travel faster and farther, but for now the stars remain out of reach with our current technology. Achieving faster-than-light travel is a concept that has fascinated scientists and science fiction enthusiasts for generations. According to our current understanding of physics, nothing can travel faster than the speed of light. The theory of relativity tells us that as an object approaches light speed, its mass increases, requiring more and more energy to accelerate further. But that hasn't stopped researchers from exploring theoretical ways to bypass this limit. One of the most well-known ideas is the concept of a warp drive, which would bend space-time itself. Instead of moving a spacecraft faster than light, a warp drive would move the space around the ship, allowing it to effectively skip the normal rules of travel. The Alcubierre drive is one theoretical model of a warp drive. Proposed in 1994, it suggests that by contracting space in front of a spacecraft and expanding it behind, the ship could move faster than light without actually breaking any physical laws. However, this would require enormous amounts of exotic matter, or negative energy, resources we currently don't know how to produce. Another concept is the idea of wormholes, which are hypothetical shortcuts through space-time. In theory, a wormhole could connect two distant points in space, allowing a spacecraft to travel between them almost instantaneously. While intriguing, wormholes remain purely theoretical and come with their own set of challenges, including instability and the need for exotic matter. Tachyons, theoretical particles that could move faster than light, have also been suggested as a way to explore faster-than-light travel. However, there's no evidence that tachyons exist, and if they did, they would behave in ways that defy our current understanding of physics. One of the biggest hurdles to faster-than-light travel is energy. The amount of energy required to even approach the speed of light is astronomical, and any theoretical method to exceed it would likely require more energy than we can currently produce. Overcoming this limitation would require breakthroughs in our understanding of energy and matter. There are also concerns about the effects of faster-than-light travel on time. According to relativity, traveling faster than light could lead to time paradoxes, such as traveling back in time. This raises questions about the fundamental nature of cause and effect in the universe. Despite these challenges, the idea of faster-than-light travel remains a subject of serious scientific inquiry. While we are far from making it a reality, some physicists believe that future discoveries could open new pathways. Theoretical research continues to explore the boundaries of our understanding of space and time. The search for faster-than-light travel also drives innovation in other areas. Even if we never achieve light-speed travel, the exploration of these ideas pushes the boundaries of our current technology and deepens our understanding of the universe. Some scientists suggest that there might be unknown laws of physics yet to be discovered that could make faster-than-light travel possible. Just as quantum mechanics and relativity transformed our understanding of the universe, future breakthroughs could reveal new ways to explore the cosmos. While faster-than-light travel remains speculative, it symbolizes humanity's desire to explore the farthest reaches of space. The dream of reaching other star systems in a human lifetime drives much of our scientific curiosity, pushing us to think beyond what is currently possible. For now, faster-than-light travel exists only in the realm of theory and imagination, but as history has shown, today's science fiction can become tomorrow's reality. The question remains, will we one day find a way to break the cosmic speed limit, or will the speed of light forever remain the ultimate barrier to our exploration of the stars? Time dilation is a fascinating consequence of Einstein's theory of relativity. It occurs when an object moves close to the speed of light, causing time to pass more slowly for that object relative to someone at rest. For space travelers, this could mean that while only a few years pass for them, decades or even centuries might pass on Earth. This effect becomes more pronounced the closer you get to the speed of light. At 90% of light speed, time for the traveler would pass at about half the rate it does for someone on Earth. If we ever develop spacecraft capable of near-light speed travel, time dilation could allow astronauts to journey far into the cosmos while only aging a few years. Time dilation has already been observed in real-world experiments. GPS satellites, for example, move fast enough that they experience a small amount of time dilation compared to people on Earth. Their clocks have to be adjusted to account for this, or the GPS system would quickly become inaccurate. One of the key ideas behind time dilation is that time and space are linked. As an object's speed increases, time slows down relative to stationary observers. This strange effect is a fundamental part of the universe's structure, governed by the speed of light as the ultimate cosmic speed limit. Relativity also predicts that time dilation could occur in the presence of strong gravitational fields. The stronger the gravity, the slower time passes. This means that near massive objects like black holes, time could slow down dramatically compared to regions of space with weaker gravitational forces. For space travel, time dilation presents both opportunities and challenges. On one hand, it could allow for long interstellar journeys without aging the crew too much. But on the other, it means that by the time they return to Earth, the world they left behind could be vastly different, with years or even centuries having passed. One of the most interesting implications of time dilation is that it could, in theory, allow humans to travel to distant stars within their lifetimes, even if faster-than-light travel remains impossible. As long as a spacecraft can approach the speed of light, the travelers on board could cover vast distances without experiencing the long passage of time. However, time dilation creates significant challenges for communication. For a near-light-speed journey, the difference in time experienced by the crew and by people on Earth would make real-time communication nearly impossible. Messages sent back and forth could take years to arrive. Relativity shows us that time is not the fixed, constant thing we once thought it was. It's fluid, depending on how fast you're moving and how strong the gravity is around you. For future space travelers, this will fundamentally change how we think about time on long journeys through space. As we consider the possibilities of time dilation, it also raises profound questions about human life and relationships. What would it mean for astronauts to return from a mission, only to find that everyone they knew has aged or passed away? The psychological and emotional effects of time dilation could be as significant as the physical ones. While time dilation might seem like science fiction, it's rooted in real physics. As we push the boundaries of space travel, these effects will become more important in planning missions and understanding what astronauts might experience on long-duration trips. Understanding time dilation and relativity is crucial for any future deep space exploration. Whether or not we ever reach near-light speeds, these principles will continue to shape how we think about time, space, and the nature of the universe itself. Navigating vast cosmic distances presents one of the greatest challenges in space exploration. Unlike on Earth, where landmarks and coordinates help guide our journeys, space is an enormous, mostly empty expanse. With no roads or reference points, spacecraft rely on advanced technology and precise calculations to find their way. One of the most important tools for navigation in space is the use of stars and celestial bodies. Much like sailors used stars to navigate the oceans, spacecraft can use distant stars as fixed reference points. These stars provide a stable guide for orientation and trajectory adjustments. Another method involves using the gravitational fields of planets and moons. By carefully planning a spacecraft's route, mission planners can use gravity assists to slingshot the spacecraft, increasing its speed and altering its direction. This technique has been used in many missions, including those to outer planets like Jupiter and Saturn. Deep space missions also rely on precise timing and communication with Earth. Spacecraft send signals back to Earth, where ground-based systems can track their position with incredible accuracy. However, the vast distances involved mean that signals take time to travel, creating delays that must be factored into navigation. The further a spacecraft travels, the more important autonomous navigation becomes. At great distances, the delay in communication with Earth can make real-time adjustments impossible. Spacecraft must be equipped with advanced onboard systems capable of making decisions and course corrections independently. Interstellar navigation presents even more daunting challenges. The distances between stars are so vast that the slightest error in trajectory could result in a spacecraft missing its target by millions of miles. Navigating such distances requires unparalleled precision and long-term planning. As we look toward future missions, new technologies are being developed to improve deep space navigation. Pulsar-based navigation, for example, uses the regular emissions from pulsars, highly magnetized, rotating neutron stars, to help pinpoint a spacecraft's location in space. This method could one day serve as an interstellar GPS. Another concept involves the use of laser beacons. By placing laser stations throughout space, spacecraft could navigate by following a series of beams, much like planes follow radio signals. This technology is still in its infancy, but it could revolutionize how we travel through space. Cosmic navigation is not just about finding the right path, it's also about avoiding potential hazards. Space is filled with debris, asteroids, and comets that could pose threats to spacecraft. Advanced sensors and detection systems are critical for identifying and avoiding these dangers. Fuel efficiency is also a key consideration in space navigation. Without the ability to refuel in space, spacecraft must carefully manage their fuel supply. Plotting the most efficient course, often using gravity assists, helps ensure that the spacecraft has enough fuel to reach its destination and complete its mission. Navigating these immense distances requires long-term thinking. Missions that span decades must anticipate changes in space conditions, such as shifts in planetary orbits or the effects of solar radiation. Continuous monitoring and adjustment are necessary to keep spacecraft on track. Ultimately, successful navigation in space comes down to a combination of technology, precision, and adaptability. As we venture farther into the cosmos, mastering the art of space navigation will be essential to reaching distant worlds and exploring the farthest reaches of our universe. Radiation exposure is one of the most significant dangers astronauts face beyond Earth's magnetosphere. Earth's magnetic field acts as a shield, protecting us from the majority of harmful cosmic rays and solar radiation. Once a spacecraft moves beyond this protective bubble, radiation levels increase dramatically. Cosmic rays, high-energy particles from outside our solar system, pose a serious threat. These particles can penetrate spacecraft walls and human tissue, increasing the risk of cancer, radiation sickness, and other health issues. Prolonged exposure, such as on long-term missions, raises the stakes even higher. Solar radiation from the sun is another concern. Solar flares and coronal mass ejections can release intense bursts of radiation that can be deadly if an astronaut is exposed. Predicting these solar events is critical, but they remain difficult to fully anticipate. One of the challenges with radiation in space is that it's not uniformly distributed. Different regions of space and different phases of the solar cycle expose astronauts to varying levels of radiation. This makes it harder to design one-size-fits-all protective measures for deep space travel. Current spacecraft are designed with some shielding, but it's not enough to fully protect against high levels of cosmic radiation. Traditional materials like aluminum can only block a portion of the radiation, and adding more layers increases the spacecraft's weight, which is already a significant constraint. Research is underway to explore new materials for radiation shielding. Some ideas include using hydrogen-rich materials, which are more effective at absorbing radiation. Others suggest that water, which is already necessary for life support, could be stored in ways that help shield astronauts from harmful rays. Another approach is to develop magnetic shields that mimic Earth's magnetosphere. By generating a magnetic field around the spacecraft, we could potentially deflect harmful radiation. However, the technology for such a shield is still in its early stages and faces considerable engineering challenges. Radiation doesn't just affect the astronauts. It can also damage electronic systems. High-energy particles can interfere with or even destroy critical spacecraft components. As we move beyond Earth's protective shield, ensuring that both the crew and the spacecraft systems are resilient to radiation becomes increasingly important. One of the most significant concerns for missions to Mars or beyond is the cumulative effect of radiation exposure. A journey to Mars could take months, with astronauts exposed to higher radiation levels the entire time. Over such a long period, even low doses of radiation can add up to dangerous levels. For deep space habitats, radiation shielding will be a top priority. If we hope to establish long-term bases on the Moon, Mars, or elsewhere, these habitats will need to offer robust protection. Some proposals suggest building habitats underground or using regolith, the local soil, as a natural shield. Medical interventions may also be a part of the solution. Scientists are researching pharmaceuticals that could help the body repair radiation damage or even prevent some of the negative effects of exposure. These advances could be critical for the health of astronauts on long missions. Ultimately, managing radiation exposure will be one of the key challenges as we venture further into deep space. As we prepare for longer journeys and more distant destinations, understanding and mitigating the risks posed by cosmic and solar radiation will be crucial to ensuring the safety of future explorers. Isolation in deep space presents unique psychological challenges for astronauts. Being cut off from Earth for extended periods can lead to feelings of loneliness, anxiety, and depression. The vast distance, combined with the long duration of missions, intensifies these effects. One of the primary concerns is the lack of real-time communication with loved ones. As spacecraft travel farther from Earth, the communication delay grows, making conversations feel disconnected and impersonal. This can increase feelings of isolation, especially on missions lasting months or years. Living in confined spaces with the same crew members for extended periods adds another layer of stress. The lack of privacy and constant proximity to others can strain relationships, leading to interpersonal conflicts. Managing group dynamics in such environments is crucial to maintaining a healthy team. Astronauts on long missions may also experience sensory deprivation. The monotony of the space environment, with no new sights, smells, or sounds, can affect mental well-being. Over time, the lack of variety can contribute to feelings of boredom and mental fatigue. Sleep disruption is another common issue. The absence of a natural day-night cycle can interfere with circadian rhythms, making it harder for astronauts to get restful sleep. Poor sleep can exacerbate stress, impair cognitive function, and contribute to emotional instability. The sense of isolation is often compounded by the psychological distance from Earth. Knowing that help is far away, and that returning home could take months or even years, can weigh heavily on astronauts' minds. This sense of remoteness can lead to feelings of vulnerability and helplessness. Astronauts are trained to handle stress, but the mental health effects of long-duration missions in deep space are still not fully understood. Each individual may react differently to isolation, and some may be more resilient than others. Monitoring mental health will be as important as managing physical health. Regular communication with Earth, even if delayed, can provide emotional support. Crew members can stay connected with their families, friends, and mission control through messages, helping to maintain a sense of connection to home. Even pre-recorded video messages can boost morale. Technology may play a role in mitigating the psychological effects of isolation. Virtual reality could simulate environments from Earth, providing astronauts with a temporary escape from the confined space of the spacecraft. This technology might offer a way to reduce feelings of confinement and offer mental relief. Another strategy is to create meaningful work and personal routines. Structured tasks and activities can help astronauts maintain a sense of purpose and focus. Regular exercise, hobbies, and creative outlets can be vital in keeping morale high during long periods of isolation. Support from fellow crew members is essential. Encouraging teamwork, cooperation, and open communication can help build a sense of camaraderie. When astronauts feel supported by their colleagues, they are better able to cope with the challenges of isolation. The psychological challenges of deep space isolation are significant, but they can be managed with careful planning, mental health support, and a focus on teamwork. As missions grow longer and distances increase, addressing the mental well-being of astronauts will be critical to their success and safety. Prolonged exposure to zero gravity presents significant challenges to the human body. Without the pull of gravity, many of the body systems begin to adapt in ways that can be harmful over time. Muscles and bones, in particular, are among the most affected. In zero gravity, muscles don't have to work as hard to move or support the body. Over time, this leads to muscle atrophy, where muscles weaken and shrink from lack of use. Astronauts on long-duration missions need to exercise regularly to counteract this effect, but even daily workouts can't completely prevent muscle loss. Bone density also decreases in zero gravity. On Earth, gravity constantly stresses the bones, helping them maintain their strength. In space, with no gravitational force acting on the body, bones begin to lose minerals, leading to a condition similar to osteoporosis. This makes astronauts more susceptible to fractures and other bone injuries. The cardiovascular system undergoes changes as well. In space, fluids in the body shift upwards, causing facial puffiness and a decrease in leg volume. Over time, the heart, which no longer has to pump against gravity, can weaken, reducing its efficiency. This poses a risk for astronauts when they return to Earth's gravity. One of the less visible effects is the impact on eyesight. Many astronauts experience changes in their vision during long space flights, often due to increased pressure on the optic nerve from fluid buildup in the head. This condition, known as spaceflight-associated neuroocular syndrome, is still being studied to fully understand its causes and long-term effects. The immune system also weakens in space. Prolonged zero gravity seems to impair the body's ability to fight off infections, making astronauts more vulnerable to illnesses. This reduced immune function is a major concern for long missions, especially if astronauts are exposed to unknown microbes on distant planets. The vestibular system, which helps maintain balance and orientation on Earth, becomes disoriented in zero gravity. Without the familiar cues of up and down, astronauts can experience space motion sickness in the early days of a mission. Although most adjust after a short period, the lack of gravity continues to affect their sense of movement. Prolonged zero gravity can also impact mental health. The physical discomforts of muscle and bone loss, combined with the unusual environment, can contribute to stress and anxiety. Physical changes are often paired with psychological challenges, making space a harsh environment for human life. One of the most concerning long-term effects is the difficulty astronauts face when they return to Earth. After months in zero gravity, their muscles and bones are often so weakened that they struggle to stand or walk. Intensive rehabilitation is required to help them regain strength and function. NASA and other space agencies are working on countermeasures to mitigate these effects. Advanced exercise equipment, better dietary supplements, and even artificial gravity environments are being explored as ways to preserve the health of astronauts on long-duration missions. Artificial gravity, created by spinning a spacecraft or a section of it, could help simulate the effects of gravity on the body. While still in the experimental phase, this concept holds promise for reducing the impact of zero gravity on future deep space travelers. Despite these challenges, the human body is remarkably adaptable. With the right interventions and support, astronauts can endure and overcome the effects of zero gravity, making long-duration space travel more feasible. However, understanding and mitigating these effects will be essential for successful missions to Mars and beyond. Storing enough food and water for long space voyages presents a critical challenge. In deep space, there are no opportunities to resupply, meaning astronauts must carry everything they need with them. This requires careful planning to ensure there is enough nourishment and hydration for the entire journey. Spacecraft have limited storage capacity, so food must be compact and lightweight. Most food for space missions is dehydrated or freeze-dried to reduce weight and preserve its shelf life. This allows astronauts to carry large quantities of food in a small amount of space, with water added later to rehydrate meals. Water, on the other hand, cannot be significantly reduced in weight or volume. Every drop of water that astronauts drink, use for hygiene, or add to food must be stored on board or recycled. Since water is heavy and takes up valuable space, efficient storage and recycling systems are essential. Recycling water is a key part of making long space missions possible. Modern spacecraft are equipped with systems that can filter and purify water from urine, sweat, and condensation, making it safe to drink again. These systems dramatically reduce the amount of fresh water that needs to be stored at the start of the mission. The challenge with food isn't just about quantity, but also nutrition. Astronauts need a balanced diet to maintain their health in the harsh conditions of space. Space food must be carefully designed to provide the right mix of vitamins, minerals, and calories to support long-term physical and mental health. Another concern is the degradation of nutrients over time. Long missions require food that can last for months or even years without losing its nutritional value. Space agencies are researching ways to fortify food or develop new preservation methods to ensure astronauts receive adequate nutrition throughout the mission. Taste and variety are also important factors. Eating the same meals over and over can lead to menu fatigue, which can reduce appetite and lead to nutritional deficiencies. Offering astronauts a variety of flavors and textures helps keep meals enjoyable and encourages them to eat properly. Astronauts on longer missions may need to grow some of their own food. Experiments in growing plants in space have already begun, with successful trials of crops like lettuce and radishes aboard the International Space Station. Growing fresh food would not only improve nutrition, but also provide a psychological boost through the presence of living plants. Hydroponics and other soil-free growing methods are being explored as potential ways to cultivate food in space. These systems use less water and space than traditional farming methods, making them ideal for the limited environment of a spacecraft or a future Martian habitat. Food packaging is another consideration. It needs to protect the food from the vacuum of space and prevent contamination, while also being lightweight and easy to store. Packaging that can be reused or recycled is preferable, as waste management is a major concern on long voyages. Innovations in food technology could also help reduce the need for bulky storage. Scientists are exploring options like lab-grown meat or nutrient-dense meal replacements that could provide astronauts with all the sustenance they need in a smaller, more efficient form. Ensuring astronauts have enough food and water for long space voyages is about more than survival. It's about maintaining health, morale, and mental well-being. As missions grow longer and more ambitious, advances in food and water storage will be essential to keeping crews safe and strong. Space is a hazardous environment, and one of the primary concerns for any mission is protecting the crew from the dangers that exist beyond Earth. Tiny meteoroids and space debris are constantly moving at high speeds through space, and even small particles can cause significant damage if they strike a spacecraft. A meteoroid the size of a grain of sand can hit with the force of a bullet because of the incredible speeds at which objects move in space. The spacecraft's hull needs to be strong enough to withstand these impacts without adding too much weight. Layers of shielding, often made from specialized materials, are used to absorb and deflect these potential dangers. One method used for protection is called Whipple shielding. It consists of multiple thin layers of metal or other materials spaced apart. When a meteoroid strikes the first layer, it breaks apart into smaller pieces, which are then easier for the inner layers to absorb. This design is effective in minimizing damage from small, fast-moving particles. Larger debris poses a different kind of threat. While less common, objects several centimeters wide or bigger could cause catastrophic damage if they collided with a spacecraft. That's why missions are carefully planned to avoid known debris fields, and space agencies monitor larger objects in orbit to track potential collision risks. Radiation is another invisible hazard. Cosmic rays and solar radiation can penetrate the spacecraft and harm both the crew and onboard systems. Shielding against radiation often involves materials like polyethylene or even water, which can help block some of the harmful particles. Spacecraft design also incorporates safe zones, or radiation shelters, where astronauts can retreat during periods of increased solar activity, such as solar flares. These areas are equipped with extra shielding to protect the crew from sudden spikes in radiation exposure. Spacesuits also need to provide protection from these hazards during spacewalks. In addition to shielding astronauts from the vacuum of space, modern suits are designed to guard against micrometeoroids and the extreme temperatures they may face outside the spacecraft. The potential for mechanical failure or environmental hazards means astronauts must be ready for emergencies at all times. Escape systems and contingency plans are in place to deal with sudden crises, including collisions or life support system failures. Fire is another unexpected hazard in space. While there's no atmosphere in the vacuum of space, fires can still occur inside the spacecraft due to faulty equipment or other causes. Special fire suppression systems and protocols are in place to prevent and quickly extinguish any flames. Spacecraft are equipped with backup systems for every critical function, including life support, navigation, and propulsion. If one system fails, another can take over to ensure the crew's safety. Redundancy is key in managing the risks posed by space hazards. Even the psychological toll of constantly facing these dangers must be managed. Training astronauts to remain calm and focused in high-stress situations is crucial. Their ability to think clearly under pressure can be the difference between disaster and survival. As we look toward more distant missions, such as to Mars or beyond, the importance of shielding and protection from space hazards will only grow. With travel times extending over months or years, the need for durable, reliable defenses becomes even more critical to the success and safety of the crew. Solar power is one of the most effective and reliable energy sources for spacecraft. In space, without the interference of Earth's atmosphere, sunlight is more intense and can be harnessed with greater efficiency. Solar panels have been used on countless missions, providing a steady stream of energy to power systems and instruments. The advantage of solar power in space is that it's renewable. As long as a spacecraft remains in the vicinity of the sun, it can generate electricity continuously without needing fuel. This makes solar power an ideal choice for missions that require long durations and sustainable energy sources. Solar panels on spacecraft are made from photovoltaic cells, which convert sunlight directly into electricity. These cells are similar to the ones used in solar panels on Earth, but they are optimized for space conditions, designed to be lightweight and durable against the harsh environment of space. One of the main challenges with solar power in space is distance from the sun. The farther a spacecraft travels from the sun, the less energy its panels can generate. This limitation becomes particularly significant for missions to the outer planets, where sunlight is much weaker. To compensate, spacecraft often carry large arrays of solar panels to capture as much sunlight as possible. These arrays can be deployed after launch and adjusted to ensure they face the sun at all times, maximizing energy production even as the spacecraft moves. Space missions like those to Jupiter or Saturn often use additional power sources, such as nuclear generators, to supplement solar power when sunlight becomes too weak. For closer missions, like those around Earth or to Mars, solar power remains the primary energy source. The efficiency of solar panels has improved dramatically over the years. Modern panels can convert more sunlight into electricity than earlier versions, allowing spacecraft to operate more powerful instruments and systems with less surface area covered by panels. Heat management is another factor. In space, solar panels can heat up quickly when exposed to direct sunlight. Managing this heat to avoid damaging the panels or reducing their efficiency is critical for long-term power generation. Solar power also enables space stations, like the International Space Station, to function continuously. The ISS has large solar arrays that supply electricity for life support systems, experiments, and communication. Without solar power, maintaining a permanent human presence in space would be far more difficult. Another application of solar power is the concept of solar electric propulsion. This system uses solar energy to power ion thrusters, enabling spacecraft to accelerate gradually over time. It's a fuel-efficient method of propulsion, particularly useful for deep space missions. In the future, advanced solar technologies might include solar sails, which use light from the sun not just to generate electricity, but also to propel spacecraft by capturing the momentum of photons. This could provide a method of long-duration travel without the need for traditional fuel. As solar panel technology continues to evolve, it will likely remain a cornerstone of space exploration. Its ability to provide clean, renewable energy makes it indispensable for current and future missions, from Earth orbit to the outer edges of the solar system. Nuclear power has emerged as one of the most reliable energy sources for space missions, especially for journeys far from the sun. Unlike solar power, nuclear energy doesn't rely on proximity to a star and can provide consistent power regardless of location. This makes it particularly valuable for missions to the outer planets or deep space. One of the most common nuclear technologies used in space is the radioisotope thermoelectric generator, or RTG. RTGs convert heat generated by the natural decay of radioactive materials, such as plutonium, into electricity. These generators have been used successfully in missions like Voyager, Cassini, and the Mars rovers. The advantage of RTGs is their longevity. The radioactive decay process is slow and steady, allowing RTGs to provide power for decades. This is critical for missions that operate far beyond Earth, where solar energy is weak or inconsistent, or in environments like the shadowed regions of the Moon. Nuclear reactors, another form of space nuclear power, offer even greater potential. While RTGs are great for low-power, long-duration missions, nuclear reactors can generate significantly more energy. This opens the door for larger spacecraft, more complex systems, and even human habitats on distant planets. One of the key benefits of nuclear power in space is its ability to provide energy in harsh environments. Whether on the cold, dark surface of a distant moon or deep within a shadowed crater, nuclear power can keep systems running continuously, where solar panels would fail. Safety is a major concern when it comes to nuclear power in space. Engineers must ensure that the radioactive materials are securely contained, both during the mission and in the event of a launch failure. Extensive testing and shielding measures are in place to prevent any contamination. Another challenge is the heat generated by nuclear power systems. In space, where there's no atmosphere to dissipate heat, spacecraft must have systems in place to manage this excess energy. Radiators are often used to release the heat into space, preventing the spacecraft from overheating. Nuclear power has proven particularly valuable for landers and rovers exploring planetary surfaces. These vehicles can operate through long Martian nights, or in areas where sunlight is limited. The Curiosity rover, for example, has been powered by an RTG, allowing it to function long after its solar-powered predecessors. For future missions, nuclear power could play an even more central role. Human missions to Mars, for example, would likely depend on nuclear reactors for life support, habitat energy, and propulsion. These reactors could provide the energy needed to sustain a human presence for extended periods. Nuclear propulsion is another exciting area of research. By using nuclear reactors to heat a propellant, spacecraft could achieve much higher speeds than conventional chemical rockets, drastically reducing travel time to distant planets or even other star systems. While there are still challenges to overcome, particularly in terms of safety and development costs, nuclear power remains one of the most promising technologies for the future of space exploration. Its ability to provide reliable, long-lasting energy makes it indispensable for deep space missions. As we continue to push the boundaries of human space travel, nuclear power will likely be a cornerstone of those efforts, providing the energy needed to explore the most distant and inhospitable corners of our solar system and beyond. Harnessing cosmic energy, such as dark energy, represents one of the most speculative and intriguing possibilities for the future of space travel. Dark energy, which is believed to make up about 70% of the universe, is a mysterious force responsible for the accelerated expansion of the cosmos. Understanding and utilizing this energy could revolutionize space exploration. The challenge lies in the fact that dark energy is still poorly understood. Scientists know it exists based on the behavior of galaxies, but its exact nature remains elusive. If we could unlock the secrets of dark energy, it might provide an almost limitless source of power for spacecraft, eliminating the need for conventional fuel. Harnessing cosmic energy could offer propulsion systems unlike anything we've seen before. Instead of carrying fuel or relying on solar power, spacecraft could theoretically tap into the very energy that drives the universe's expansion. This would allow for sustained travel over vast distances, without the constraints of current technology. In addition to dark energy, there's the concept of zero-point energy, a form of energy thought to exist in the fabric of space itself. The idea suggests that even in a vacuum, fluctuations in quantum fields create a base level of energy. If tapped, zero-point energy could offer a continuous source of power for interstellar missions. However, these concepts are still largely theoretical. Extracting usable energy from dark energy or zero-point energy would require breakthroughs in physics that we haven't yet achieved. We would need to develop entirely new technologies and understand more about the fundamental forces governing the universe. Another idea is the potential use of cosmic radiation as a power source. High-energy particles travel through space at nearly the speed of light, and if captured effectively, they could be converted into usable energy. This would allow spacecraft to harvest energy as they travel through the cosmos. Beyond propulsion, harnessing cosmic energy could change how we think about sustaining life in space. Instead of relying on stored energy sources, habitats and life support systems could continuously draw power from the universe itself, making long-term missions more feasible. The idea of tapping into cosmic forces also raises profound questions about the future of humanity's role in the universe. If we could harness the energy driving the cosmos, it would signify a level of technological advancement far beyond what we currently possess. It could make interstellar colonization a reality, However, there are potential risks involved in manipulating forces like dark energy. Since we understand so little about it, attempting to control or extract it could have unintended consequences. Some scientists caution that tampering with the very fabric of the universe might be more dangerous than beneficial. Despite these challenges, the pursuit of cosmic energy continues to captivate researchers and visionaries. The promise of nearly limitless energy has driven some of the most ambitious theories in modern physics. And even if dark energy remains out of reach, the journey to understand it will undoubtedly lead to new discoveries. For now, harnessing cosmic energy remains in the realm of science fiction, but with each passing year, our understanding of the universe deepens. As we continue to explore the mysteries of space, we might one day discover the keys to unlocking the vast, untapped energy all around us. Should we ever achieve the ability to harness these cosmic forces, it would mark a new era in human exploration, allowing us to travel farther and faster than ever before. The universe itself could become the fuel for our journey through the stars. Energy storage in space presents a significant challenge for long-duration missions. Spacecraft need reliable energy sources to power life support systems, propulsion, and scientific instruments. However, storing energy efficiently and safely in space is far more complicated than on Earth. One of the primary issues is the lack of stable environments. In space, temperatures can fluctuate drastically, depending on whether the spacecraft is in sunlight or shadow. These extreme temperature changes can affect the performance and longevity of batteries and other energy storage systems. Traditional batteries are commonly used to store energy in space, but they have limitations. Batteries degrade over time, especially in the harsh environment of space, reducing their ability to hold a charge. This poses a problem for missions that need to last for years or even decades without maintenance. Another issue with batteries is their weight. The more energy a spacecraft needs, the more batteries it must carry, which adds mass to the mission. Increased mass requires more fuel for launch, making it less efficient for long journeys where weight is a critical factor. Thermal management is also a significant concern. In the vacuum of space, there's no atmosphere to dissipate heat generated by energy storage systems. Without proper cooling, batteries and other systems can overheat, leading to reduced efficiency or failure. Solar power, while abundant in certain regions of space, doesn't always provide a continuous energy source. Spacecraft often need to store energy during periods when solar panels are inactive, such as during eclipses or while traveling through the shadow of a planet. Energy storage systems must be able to bridge these gaps without compromising the mission. Advanced energy storage solutions, such as supercapacitors, are being explored as alternatives to traditional batteries. Supercapacitors can charge and discharge rapidly and have longer lifespans, but they typically store less energy than batteries, which limits their use in long-term space missions. Another potential solution involves flywheel energy storage, which stores energy by spinning a rotor at high speeds. Flywheels are more durable and less affected by temperature fluctuations, but they are complex and require precision engineering to operate reliably in space. Energy storage systems must also be resistant to radiation. In deep space, where there's no protective atmosphere, radiation from cosmic rays and solar particles can damage sensitive electronics and degrade storage systems. Shielding against radiation is crucial, but it adds weight and complexity to spacecraft designs. For interplanetary missions, energy storage needs are even greater. Spacecraft traveling to distant planets may spend extended periods without access to solar power. Systems must be able to store enough energy to last through long stretches of darkness or low solar intensity. Nuclear power sources, like radioisotope thermoelectric generators, provide an alternative that doesn't rely on sunlight. While they offer continuous power, they still require safe and efficient ways to store the energy they generate for use during peak demand periods. In the future, new energy storage technologies such as advanced chemical batteries or fusion-based systems could help solve these challenges. These innovations will be essential for making deep space missions, including human exploration of Mars, more feasible. Overcoming the challenges of energy storage in space will require creative solutions and cutting-edge technology. As missions become longer and more ambitious, the need for reliable, efficient energy storage systems will be critical to sustaining life and exploration far from Earth. Space-based fuel production could be a game-changer for long-duration missions and interplanetary travel. Instead of carrying all the necessary fuel from Earth, spacecraft could refuel at key points during their journey. This concept could reduce launch costs and extend the range of missions. One of the most promising ideas is to extract fuel from resources found in space. Water, for example, can be broken down into hydrogen and oxygen, the key components of rocket fuel. By mining water from the Moon or asteroids, future missions could create fuel stations in space. The Moon is a prime candidate for space-based fuel production. Its poles contain deposits of water ice, which could be harvested and processed into fuel. Establishing lunar fuel depots would make missions to Mars and beyond more efficient, as spacecraft could refuel after leaving Earth's orbit. Asteroids also hold potential for fuel production. Many contain water ice and other valuable minerals. By setting up mining operations on asteroids, spacecraft could extract the necessary resources to generate fuel for extended missions or return trips to Earth. Fuel production in space could also take advantage of solar energy. Solar-powered electrolysis systems could split water into hydrogen and oxygen, providing a sustainable way to produce fuel. This would reduce the need for heavy, complex infrastructure and make fuel production more scalable. Mars presents another opportunity for in-situ fuel production. The planet's atmosphere is rich in carbon dioxide, which could be converted into methane fuel using the Sabatier process. This would allow future missions to produce the fuel they need for the return trip to Earth, without having to carry it from the start. Developing fuel on Mars would be critical for human exploration and colonization. It would lower the cost of missions by reducing the amount of fuel required at launch, making sustained human presence on the planet more feasible. Space-based fuel production would also enable reusable spacecraft to be more practical for deep space missions. By refueling in orbit or on other celestial bodies, spacecraft could make multiple trips without returning to Earth for more fuel, increasing the efficiency and flexibility of space travel. Challenges remain, however. Mining and processing resources in space is still a developing field, and the technology to efficiently extract water or other materials from the Moon or asteroids needs to be perfected. There's also the issue of transporting and storing the fuel once it's produced. Safety is another concern. Handling and storing large amounts of volatile rocket fuel in space comes with risks, and ensuring that fuel production and storage systems are reliable and secure will be essential for the success of these operations. Despite these challenges, the potential benefits of space-based fuel production are immense. It could open the door to more ambitious missions, enabling humanity to explore the solar system and beyond without being limited by the amount of fuel that can be carried from Earth. If we can successfully harness the resources of the Moon, Mars, and asteroids, space-based fuel production could mark the beginning of a new era in space exploration. Missions that once seemed impossible could become routine, powered by the vast resources waiting to be tapped in space. Deep space stations and bases represent the next step in humanity's journey into the cosmos. These outposts would serve as waypoints for missions traveling farther from Earth, offering places to refuel, resupply, and rest. Establishing these stations would be critical for exploring the Moon, Mars, and beyond. The idea of a permanent space station orbiting beyond Earth is not new. The International Space Station has shown that humans can live and work in space for extended periods. However, stations farther from Earth would face different challenges, such as harsher environments and longer supply lines. A deep space station could be placed at a stable point between the Earth and Moon, like the lunar Lagrange points. These points allow a station to remain fixed in position, serving as a hub for missions to the Moon or Mars. This would make lunar exploration more efficient, with supplies and fuel available nearby. Bases on the Moon would be a natural extension of this idea. A lunar base could support scientific research, mining operations, and fuel production. The Moon's resources, such as water ice, could sustain both the base itself and future missions deeper into space. Mars, too, could eventually host human bases. These bases would serve as long-term habitats, offering astronauts protection from the harsh environment. They could also act as launching points for missions to the outer planets, reducing the need for Earth-based launches. Building these stations and bases requires careful consideration of life support systems. Bases would need to recycle air, water, and waste efficiently to support a permanent crew. Systems that can run autonomously without constant resupply from Earth are essential for long-term success. Radiation protection is another key factor. In deep space, astronauts are exposed to higher levels of cosmic radiation. Stations and bases would need advanced shielding to keep crews safe from this threat, especially on the Moon or Mars, where there's little natural protection. Energy is also a major consideration. Deep space stations would need reliable power sources, such as nuclear reactors or advanced solar panels. Bases on the Moon or Mars could take advantage of local resources like sunlight or geothermal energy to generate the power needed for life support, research, and exploration. These outposts would also need to be self-sufficient in terms of food production. Growing food in space or on the surface of other planets would reduce reliance on supply missions from Earth. Hydroponic or aeroponic systems could allow astronauts to grow crops even in the most hostile environments. Establishing communication networks will be crucial for the success of deep space stations. With distances growing as missions travel farther from Earth, maintaining contact with mission control will require advanced communication systems capable of handling time delays and high data rates. Robotic systems will likely play a key role in maintaining and expanding these stations. Robots can handle many of the routine tasks, such as repairs and construction, reducing the workload for human crews. Autonomous systems could also prepare sites on the Moon or Mars before humans arrive. Deep space stations and bases would serve not only as operational hubs, but also as symbols of human progress. They represent a commitment to expanding our presence in the solar system, creating a network of outposts that push the boundaries of exploration. Each station brings us one step closer to becoming a multi-planetary species. Building habitats on asteroids or planets is one of the most ambitious goals for future space exploration. These habitats would allow humans to live and work in environments far from Earth, supporting long-term missions and potentially even permanent settlements. The design and construction of such habitats require innovative solutions to deal with the challenges of space. On asteroids, habitats would need to be anchored securely. Unlike planets, asteroids have very little gravity, making it difficult for structures to stay in place. Engineers would need to develop systems to anchor habitats to the surface, or possibly even burrow into the asteroid itself to protect the structure and its inhabitants. Asteroids offer some unique advantages for habitat construction. Many are rich in metals and other resources that could be used to build and maintain the habitats. Mining these materials on site would reduce the need to transport construction supplies from Earth, making the process more efficient. Building habitats on planets like Mars presents different challenges. Mars has a thin atmosphere that provides little protection from cosmic radiation, and temperatures can vary drastically between day and night. Any habitat would need to be insulated and shielded to protect astronauts from both the cold and the harmful radiation. One solution for Martian habitats is to use the planet's regolith, or surface material, as building material. Techniques like 3D printing with regolith could allow habitats to be constructed from local resources, reducing the need for materials to be sent from Earth. These structures could be designed to withstand the harsh conditions of the Martian surface. Underground habitats are another possibility for planets and moons. By building below the surface, astronauts could take advantage of the natural protection provided by the ground, which would shield them from radiation and extreme temperatures. Lava tubes on the Moon or Mars could serve as natural shelters, reducing the need for extensive construction. Life support systems in these habitats would need to be fully self-sustaining. Air, water, and food would all have to be recycled efficiently to support a permanent or semi-permanent crew. This would require advanced recycling systems and potentially in-situ resource utilization, where local materials are used to generate water or oxygen. Energy generation is another critical factor. Solar panels might work on Mars or the Moon, but farther from the Sun, other energy sources like nuclear reactors would be needed. Habitats would need reliable and robust energy systems to power life support, scientific instruments, and communication systems. The interior design of these habitats would need to prioritize both functionality and the mental well-being of the crew. Living in isolated, confined spaces for long periods can take a psychological toll, so habitats would need to be designed with space for relaxation and recreation, as well as for work and research. Habitats on planets or asteroids must also be designed for potential emergencies. Systems would need to be in place for dealing with air leaks, equipment failures, or sudden changes in the environment. Redundancy and safety protocols would be critical for ensuring the survival of the crew in the event of an unexpected crisis. In the long term, these habitats could become the foundation for colonies. If we can successfully build and sustain habitats on asteroids or planets, we could eventually expand them into larger settlements, supporting more people and more complex operations. This would represent the first step toward humans living permanently off Earth. Building habitats on other worlds is about more than just survival. It's about pushing the boundaries of human capability, demonstrating that we can not only explore space, but also thrive in its most extreme environments. These habitats will be the first homes for humans beyond Earth, marking the beginning of a new chapter in our existence. Self-sustaining biospheres in space could hold the key to long-term survival beyond Earth. These closed-loop ecosystems would recycle air, water, and nutrients to support human life indefinitely, minimizing the need for resupply missions from Earth. Creating such systems is essential for establishing permanent colonies on the Moon, Mars, or other celestial bodies. A self-sustaining biosphere must mimic Earth's natural cycles. Plants play a crucial role in this system by absorbing carbon dioxide and producing oxygen through photosynthesis. In turn, humans and animals would exhale carbon dioxide and consume the oxygen, creating a balanced exchange that keeps the air breathable. Water recycling is another critical component. Every drop of water in the biosphere would need to be reused multiple times. Advanced filtration and purification systems would be necessary to clean wastewater, including human waste, sweat, and condensation, making it safe for drinking, agriculture, and hygiene. Food production would also need to be integrated into the biosphere. Growing crops would not only provide food but also contribute to oxygen production and waste recycling. Hydroponic or aeroponic farming, where plants grow without soil, could maximize space and resource efficiency, making it possible to produce a wide variety of food in a small area. Waste management is crucial in a closed system. Organic waste from plants and animals could be composted to return nutrients to the soil or water used in farming. This ensures that the nutrients necessary for plant growth are continuously cycled through the system, supporting ongoing food production. Temperature and humidity control are vital for maintaining a stable environment. In space, external conditions can be extreme, so the biosphere would need to be well insulated and equipped with systems to regulate internal climate. This would help keep the ecosystem in balance and ensure that plants and humans can thrive. The structure of the biosphere must be carefully designed to protect it from space hazards. Micrometeoroids, radiation, and temperature fluctuations could all pose threats to the integrity of the habitat. Shielding the biosphere while maintaining access to natural light for plant growth is a complex engineering challenge. Psychological well-being is also an important consideration. Living in a closed environment for extended periods could lead to stress, anxiety, or depression. Incorporating natural elements like plants, running water, and even artificial simulations of outdoor environments could help improve the mental health of inhabitants. Biodiversity within the biosphere is essential for its resilience. Including a variety of plants, insects, and potentially small animals would help maintain a stable and healthy ecosystem. The diversity of life forms ensures that the system can adapt to changes and remain balanced over time. In space, the stakes are higher for maintaining this balance. If a component of the biosphere fails, it could quickly lead to a breakdown of the entire system. Redundancies and automated monitoring would be necessary to detect and address problems before they become critical. Research on Earth, such as the Biosphere 2 project, has provided valuable insights into how closed ecosystems function. While challenges remain, these experiments are helping scientists understand the complex interactions between organisms and their environment, offering a blueprint for future space-based biospheres. Ultimately, self-sustaining biospheres could allow humans to live independently from Earth. Whether on a space station, an asteroid, or another planet, these ecosystems would support human life for generations, marking the next great leap in our ability to explore and inhabit the cosmos. Space habitats designed for long-term human occupation will need to solve one of the biggest challenges of living in space: the absence of gravity. Without gravity, the human body experiences a range of negative effects, from muscle atrophy to bone density loss. To counteract this, creating artificial gravity in space habitats is essential. One of the most widely considered methods for generating artificial gravity is through centrifugal force. By rotating a space habitat, the centrifugal force pushes occupants toward the outer walls, mimicking the effects of gravity. The faster the rotation, the more gravity-like force is generated. The design of these rotating habitats would require careful engineering. If the rotation is too slow, the gravity effect will be weak, but if it's too fast, the occupants might experience dizziness or disorientation. Finding the right balance in rotation speed and habitat size is key to making this concept work. A torus, or ring-shaped habitat, is one common design for artificial gravity systems. In this design, the living and working areas are built along the inner edge of the ring, which spins to create a consistent gravitational effect along its walls. This setup allows inhabitants to move and live as they would on Earth. Another possibility is a cylindrical habitat that rotates along its axis. The centrifugal force generated by the spinning cylinder would create artificial gravity along the walls. This type of structure could potentially house larger populations, making it ideal for long-term space colonies. Artificial gravity would not need to be as strong as Earth's gravity to be effective. Studies suggest that even a fraction of Earth's gravity, like what exists on the Moon or Mars, could help mitigate many of the health issues caused by prolonged weightlessness. The goal would be to create a livable environment where people can stay healthy over the long term. One challenge of rotating habitats is the need to dock spacecraft. Since the habitat is spinning, docking a stationary spacecraft would require precise coordination or a specialized system to match the rotation. Engineers would need to design solutions to safely transfer cargo and people between spinning habitats and non-rotating spacecraft. Artificial gravity also raises questions about how other systems in the habitat would function. For instance, fluids, waste management, and plant growth all behave differently under varying gravitational conditions. Designing life support and agricultural systems that work well with artificial gravity would require extensive testing and innovation. For smaller space habitats, artificial gravity may not be feasible, and crews would need to rely on other countermeasures like exercise to combat the effects of weightlessness. However, for larger, permanent settlements, creating a comfortable, Earth-like gravity will be crucial for long-term habitation. Artificial gravity could also play a psychological role in making space more livable. The feeling of weightlessness, while novel at first, can become disorienting over time. A gravity-like environment could provide a sense of normalcy, helping inhabitants adjust more easily to life away from Earth. Exploring the possibilities of artificial gravity is also essential for future missions to planets with low gravity. While Mars has some gravity, it's only about 38% of Earth's, which may not be enough to maintain long-term human health. Supplementing that with artificial gravity could be an important part of sustaining colonies on other worlds. In the end, creating space habitats with artificial gravity is not just about comfort. It's about ensuring the survival and well-being of humans as we push further into the cosmos. Solving this problem will allow us to live and work in space for extended periods, opening the door to deeper exploration and, eventually, permanent settlement off Earth. As we look toward colonizing space, ethical considerations must be at the forefront of our planning. The idea of settling on other worlds presents a host of moral questions about humanity's impact on the cosmos and the responsibility we hold for our actions. How we approach space colonization will shape the future not just for our species, but for the universe around us. One of the most pressing ethical concerns is the potential contamination of other planets. Introducing Earth-based organisms to environments like Mars or Europa could disrupt any existing ecosystems, even if they are microbial. If life exists beyond Earth, we must consider whether we have the right to interfere with or even destroy those ecosystems. There's also the issue of resource exploitation. Asteroids, moons, and planets may contain valuable resources, but should we extract these materials freely? There's a moral question about whether space's resources belong to all humanity, future generations, or if they can be claimed by whoever reaches them first. The legal framework surrounding space colonization is still developing, but the ethical implications of claiming celestial bodies are complex. The Outer Space Treaty of 1967 prohibits any one nation from claiming sovereignty over celestial bodies, but it's unclear how this will apply to private companies or future settlements. We must navigate these legal and ethical waters carefully. Another consideration is the inequality that space colonization could exacerbate. If only the wealthiest nations or corporations can afford to build space colonies, it could create a new level of inequality where some have access to the resources and opportunities of space, while others are left behind on Earth. And the ethics of governance in space colonies will also be a critical issue. Who will make decisions in these new settlements, and how will laws and rights be upheld? The inhabitants of these colonies could face unique legal and moral challenges, and ensuring that their rights are protected will be essential. Environmental ethics extend beyond Earth, especially as we contemplate terraforming planets like Mars. While making a planet more habitable for humans might seem like progress, we must ask whether altering an entire world for our benefit is morally acceptable. What is our responsibility to preserve the natural state of other worlds? The potential for human expansion into space also raises questions about the treatment of future generations. Colonizing another planet would mean raising generations of people far from Earth, possibly with limited opportunities to return. The ethical implications of creating life in such isolated and potentially dangerous environments are worth serious consideration. Space colonization also brings up questions of militarization. As humans spread across the solar system, the possibility of conflicts over territory or resources becomes real. How do we ensure that space remains a domain of peaceful exploration, rather than a new frontier for war and conquest? The psychological and social challenges of living in isolated colonies are another ethical concern. Ensuring that space settlers have the support, freedom and quality of life needed to thrive will be crucial. Colonies should not become exploitative environments where people are forced to endure harsh conditions without adequate resources or care. We must also consider the ethics of who is chosen to go to space. Should everyone have an equal chance to be part of a space colony, or will access be determined by wealth, nationality, or other factors? The selection process for colonists must be fair and just, avoiding the creation of a spacefaring elite. In the end, colonizing space will reflect our values as a species. As we prepare to take this monumental step, we must think carefully about the ethical implications of our actions, ensuring that our exploration of the cosmos is guided by responsibility, justice, and respect for the universe around us. The search for exoplanets in the habitable zone has become one of the most exciting fields in astronomy. The habitable zone, often called the Goldilocks zone, is the region around a star where conditions might be just right for liquid water to exist, one of the key ingredients for life as we know it. Finding planets within this zone increases the possibility of discovering environments where life could thrive. Detecting exoplanets in the habitable zone isn't easy. Most exoplanets are too far away to be directly observed, so scientists rely on indirect methods like the transit method. This involves monitoring stars for tiny dips in brightness that occur when a planet passes in front of them. These dips can reveal a planet's size, orbit, and, importantly, whether it lies in the habitable zone. Another method, the radial velocity technique, detects the slight wobble in a star's motion caused by the gravitational pull of an orbiting planet. By measuring this wobble, scientists can infer the planet's mass and its distance from the star, helping to determine if it's in the habitable zone. The discovery of exoplanets in this zone is important, but the conditions for life require more than just the right distance from a star. The planet's atmosphere, temperature, and surface conditions also play critical roles. Researchers are developing ways to study these aspects, including analyzing the light passing through a planet's atmosphere to detect signs of water, oxygen, or methane, potential indicators of life. The type of star the planet orbits is also a crucial factor. Habitable zones around smaller, cooler stars, like red dwarfs, are much closer to the star than those around stars like our Sun. This can expose planets to intense solar flares or tidal locking, where one side of the planet always faces the star, creating extreme conditions on both the day and night sides. Some of the most promising exoplanet discoveries have been around red dwarf stars, as they are the most common type of star in the galaxy. However, scientists are cautious about declaring these planets potentially habitable without further study, as their proximity to volatile stars might make sustaining life difficult. Advancements in telescopes, such as the James Webb Space Telescope, are helping astronomers learn more about exoplanets in the habitable zone. With its ability to analyze atmospheres and detect signs of chemical compounds, Webb may provide the most detailed information yet about these distant worlds. The ultimate goal is to find an Earth-like planet. A rocky planet, similar in size to Earth, with liquid water and a stable atmosphere, would offer the best chance of harboring life. While many planets have been found in the habitable zone, the search for one that mirrors Earth's conditions continues. The discovery of even microbial life on another planet would be groundbreaking. It would answer the age-old question of whether we are alone in the universe and could revolutionize our understanding of biology and life's potential diversity across the cosmos. Exoplanets in the habitable zone are also important for future human exploration. If we ever develop the technology to travel to other star systems, these planets might be among the first targets. Finding a habitable planet could be humanity's best hope for establishing colonies beyond our solar system. However, even within the habitable zone, conditions might not be as they appear. Some planets may have thick atmospheres that trap heat, making them uninhabitable. Others could have surfaces covered in ice, despite their location. Each discovery requires careful analysis to determine if life could truly exist there. As our search continues, we grow ever closer to finding another world where life might exist. The discovery of such a planet would be one of the greatest achievements in human history, forever changing our perspective on life and the universe. Current efforts to detect extraterrestrial life are pushing the boundaries of both technology and imagination. One of the most active areas of research focuses on finding biosignatures, chemical signs that might indicate the presence of life on other planets and moons. These efforts are centered on understanding what conditions are necessary for life and where they might exist beyond Earth. Mars has been a major target in the search for extraterrestrial life. NASA's Perseverance rover is currently exploring the surface of Mars, collecting samples and searching for evidence of ancient microbial life in areas that were once thought to have held water. These samples could eventually be returned to Earth for further analysis. Beyond Mars, scientists are particularly interested in the icy moons of the outer planets, such as Europa and Enceladus. These moons are believed to have vast subsurface oceans beneath their icy crusts, which may provide the right conditions for microbial life to exist. Missions like NASA's upcoming Europa Clipper aim to study these moons in greater detail. In addition to exploring our own solar system, astronomers are using telescopes to study the atmospheres of distant exoplanets. By analyzing the light passing through an exoplanet's atmosphere, scientists can look for the presence of gases like oxygen, methane, or carbon dioxide, which on Earth are often linked to biological processes. The search for extraterrestrial life isn't just about finding microbes. Projects like SETI, the search for extraterrestrial intelligence, are scanning the skies for radio signals or other forms of communication that might indicate the presence of intelligent civilizations. SETI uses large radio telescopes to listen for patterns or anomalies that could suggest artificial signals from another species. Advances in technology have made it easier to search for life in places that were previously inaccessible. New robotic explorers, designed to withstand the extreme conditions of planets and moons, can travel farther and gather more detailed data than ever before. These missions are expanding the range of environments we can explore for signs of life. One exciting development is the use of artificial intelligence to sift through the vast amounts of data collected from space missions. AI can quickly analyze patterns and detect anomalies that might have been missed by human researchers. This technology is helping scientists find new targets in the search for extraterrestrial life. Laboratories on Earth are also working to understand what forms life might take beyond our planet. Researchers are studying extremophiles, organisms that live in extreme conditions on Earth, to learn how life could survive in the harsh environments of space, like on Mars, Europa, or Titan. Astrobiology, the study of life in the universe, is a growing field that brings together experts from many disciplines, including biology, chemistry, and planetary science. These scientists are working to answer fundamental questions about the origins of life, how it evolves, and whether it could exist elsewhere in the cosmos. In addition to government agencies, private companies are now joining the effort to find extraterrestrial life. Companies like SpaceX and Blue Origin are developing new spacecraft that could eventually help carry out missions to distant worlds, further expanding our ability to explore the universe. Public interest in the search for extraterrestrial life continues to grow. Citizen science projects, where volunteers help analyze data from telescopes or assist in research, are becoming more popular. This widespread curiosity reflects humanity's enduring desire to know whether we are alone in the universe. While we have yet to find definitive proof of life beyond Earth, every new mission brings us closer to that discovery. The search for extraterrestrial life is one of the most profound scientific endeavors of our time, and it holds the potential to answer some of the biggest questions about life and our place in the universe. The Fermi paradox is one of the most intriguing questions in the search for extraterrestrial life. It arises from the apparent contradiction between the high probability of alien civilizations existing in our galaxy and the complete lack of evidence for their existence. With billions of stars and potentially habitable planets in the Milky Way, why haven't we seen any signs of intelligent life? Enrico Fermi, the physicist after whom the paradox is named, famously asked, "Where is everyone?" If advanced civilizations are common, they should have spread across the galaxy by now, or at least left detectable signals. Yet we've observed no definitive evidence of their presence. One explanation for the paradox is that intelligent life might be exceedingly rare. While simple microbial life could be common, the development of complex intelligent life may require an extremely rare combination of events. Earth's history might be the exception rather than the rule. Another possibility is that civilizations are out there, but they are too far away or too technologically advanced for us to detect. The vast distances between stars mean that even if signals are being transmitted, they could take thousands of years to reach us, or we might not have the right technology to recognize them. It's also possible that intelligent civilizations deliberately avoid contact with us. Known as the zoo hypothesis, this theory suggests that more advanced species may be observing us from a distance, but have chosen not to interfere with our development, much like humans observing animals in the wild. Civilizations might also destroy themselves before they have the chance to explore or communicate with the cosmos. The idea that technological advancement inevitably leads to self-destruction, through war, environmental collapse, or other means, could explain why we haven't detected any extraterrestrial signals. The Great Filter theory expands on this idea, proposing that somewhere along the path from simple life to advanced civilization, there is a highly improbable step that most species do not survive. This filter could be behind us, meaning we're incredibly lucky, or ahead of us, suggesting that humanity might still face a critical challenge to its survival. Another explanation is that we're simply looking in the wrong way. Our current efforts to detect extraterrestrial life are based on the assumption that other civilizations use technologies similar to ours. However, they might communicate in ways we cannot yet comprehend, such as using advanced quantum communication or signals beyond our detection capabilities. Some researchers suggest that life might exist in forms vastly different from what we expect. Alien civilizations could be based on entirely different biochemistries, or exist in non-physical forms, such as advanced digital consciousnesses, making them difficult for us to recognize or detect. There's also the possibility that we are living in a simulation, and that the apparent absence of extraterrestrial life is part of the design. If our reality is a controlled simulation, any evidence of other civilizations might be intentionally hidden from us, adding another layer of complexity to the paradox. It's possible that civilizations are detectable for only a brief window of time. Technological societies might evolve quickly, but also destroy themselves or retreat into isolation before we have a chance to observe them. We could be missing these civilizations by mere centuries or millennia. Ultimately, the Fermi paradox reminds us of how little we truly understand about life in the universe. It pushes us to expand our thinking, explore new methods of searching, and consider possibilities that go beyond the limitations of human experience and technology. As we continue searching for extraterrestrial life, the Fermi paradox will remain a central question. Whether we are the only intelligent species, or one among many, the answer will have profound implications for our understanding of the universe and our place within it. The discovery of alien civilizations would be one of the most transformative events in human history. It would fundamentally alter our understanding of life, the universe, and our place within it. The implications would ripple through science, philosophy, religion, and culture in ways we can scarcely imagine. First and foremost, discovering alien life would provide concrete evidence that we are not alone in the universe. This confirmation would answer one of humanity's oldest and most profound questions, reshaping our perspective on life's uniqueness, or lack thereof. Such a discovery would revolutionize the field of biology. If extraterrestrial life operates on different biochemistry or evolves in ways we have not seen on Earth, it would expand the scope of what we consider possible for life. It could offer insights into the diversity of life forms that the universe can support. The discovery of an intelligent civilization would raise immediate questions about communication. How do we talk to them? What language or methods could be used to exchange ideas, given the potentially vast differences in biology, culture, and technology? There would also be political and ethical challenges. How should humanity approach contact with an alien species? Would nations cooperate or compete for the first interaction? The discovery could either unite or divide humanity, depending on how it is handled. Religious and philosophical implications would be equally profound. Many belief systems are centered around humanity's special place in the universe. Learning that intelligent life exists elsewhere might challenge some worldviews, while others could find their beliefs reinforced by this new context. The technology of an alien civilization could be far more advanced than ours. If we could learn from them, it might lead to rapid advancements in science, medicine, and engineering. On the other hand, there's the possibility that their technology could be dangerous or too complex for us to fully grasp. The risk of misunderstanding or miscommunication with an alien species is another important consideration. Even if we succeed in making contact, our assumptions about their intentions or values might be completely wrong, leading to unintended conflict or tension. There's also the possibility that alien civilizations could view humanity as a lesser species, or worse, a threat. The discovery might raise concerns about security and survival, prompting debates about whether we should attempt to communicate at all or remain silent to avoid drawing attention. If the civilization we discover is much older than ours, they might offer insights into long-term survival. We could learn from their experiences, understanding how to avoid the pitfalls that might threaten our own existence as we continue to advance technologically. Economically, the discovery of alien life could open up new possibilities for trade, but it might also introduce challenges. How would an interstellar economy function? What resources, knowledge, or goods could we possibly offer a more advanced civilization? And what risks would come with interplanetary commerce? The psychological impact on humanity would be enormous. Knowing that we are not the only intelligent species in the universe could alter how we see ourselves, our relationships, and our future. It might inspire a new age of exploration, cooperation, and scientific discovery, or, alternatively, lead to existential anxiety about our place in the cosmos. In any case, the discovery of an alien civilization would mark the beginning of a new chapter in human history. The way we handle that discovery will shape our future as a species, determining whether we become part of a larger cosmic community or remain isolated in our small corner of the universe. Deep space may be the gateway to discovering entirely new forms of life, unlike anything we have encountered on Earth. The vastness of the universe, with its countless stars and planets, suggests that life could emerge in many different ways. Exploring deep space offers the chance to find organisms that challenge our very definition of life. One of the most exciting possibilities is that life beyond Earth could be based on different chemical building blocks. While all known life relies on carbon, water, and oxygen, alien life forms might use other elements like silicon or ammonia, thriving in environments we would consider hostile. Deep space could also harbor life in places we haven't yet fully explored. Moons with subsurface oceans like Europa and Enceladus are prime candidates for finding microbial life in conditions that might be similar to early Earth. Beneath their icy crusts, oceans warmed by tidal forces could host ecosystems driven by chemosynthesis, rather than sunlight. Discovering life in deep space would not only reveal new organisms, but also offer insights into how life might evolve under different planetary conditions. Planets or moons with varying atmospheres, gravities, and temperatures could give rise to entirely new biological adaptations that we can barely imagine. Life forms that evolve in deep space environments could have fundamentally different metabolisms. For instance, organisms might derive energy not from the sun, but from cosmic radiation, geothermal vents, or chemical reactions in environments rich in methane or sulfur. Understanding these life forms would vastly expand our knowledge of biology. The discovery of extremophiles, organisms that live in the harshest conditions on Earth, has already hinted at the possibilities for life elsewhere. If life can thrive in the boiling hot springs of Yellowstone or the freezing, oxygen-poor depths of the ocean, it could potentially survive in the extreme environments of deep space as well. Space itself might host life forms that we haven't considered. The vast vacuum of space, though inhospitable by Earth standards, could contain microscopic organisms traveling between planets on asteroids or comets. These interstellar hitchhikers might represent a form of life adapted to survive the intense radiation and cold of space. The existence of such life would raise questions about the potential for panspermia, the theory that life might spread through the universe by traveling on comets or asteroids. If we discover life that appears to share common traits with Earth life, it could suggest that life here might have originated elsewhere in the cosmos. Advanced space exploration technology could allow us to find not only microbial life, but also more complex organisms. While intelligent life remains speculative, even the discovery of multicellular organisms or unique ecosystems would be a monumental achievement, offering us a glimpse of how life could develop in diverse cosmic environments. New life forms could offer practical benefits for humanity as well. Studying alien biology might lead to breakthroughs in medicine, technology, or environmental science. Organisms that thrive in harsh environments could inspire new ways to handle extreme conditions on Earth, from drought resistance to radiation protection. The possibility of encountering life in deep space also brings with it significant ethical considerations. How we study and interact with these new life forms will define our approach to space exploration. Protecting their ecosystems while learning from them will be a delicate balance that requires careful thought and planning. Deep space, with its unknown mysteries and untapped potential, offers a doorway to discovering life forms that defy our understanding of biology. Each new discovery will expand the boundaries of science and challenge our assumptions about the conditions needed for life to exist. As we continue to explore the universe, we may find that life is far more diverse and resilient than we ever thought possible. Mars has long captured the imagination of scientists and explorers as the most likely candidate for terraforming in our solar system. With its similarities to Earth, including a day length close to ours and polar ice caps, Mars presents a unique opportunity for human colonization. But to make Mars truly habitable, we would need to transform its environment dramatically. Terraforming Mars would involve altering the planet's atmosphere and surface to create conditions suitable for human life. The first step would be to increase the atmospheric pressure, which is currently less than 1% of Earth's. A thicker atmosphere would allow for liquid water to exist on the surface and provide some protection from harmful solar radiation. One idea for thickening Mars's atmosphere is to release greenhouse gases, like carbon dioxide, into the air. This would trap heat and warm the planet, potentially triggering a runaway greenhouse effect that could help melt the polar ice caps. The released water vapor would contribute to the atmosphere and create rivers, lakes, or even oceans. The challenge is that Mars has no magnetic field to protect it from solar wind, which continually strips away the atmosphere. Any attempt to terraform the planet would have to address this issue, perhaps by creating artificial magnetic fields or finding ways to continually replenish the atmosphere. Water is another critical element for terraforming Mars. While evidence suggests that Mars once had flowing water, most of it is now trapped in ice or underground. Melting this ice or extracting water from beneath the surface would be essential for supporting human life and growing crops. Introducing plants and algae to Mars is another possibility. These organisms could help generate oxygen through photosynthesis, slowly transforming the Martian atmosphere. Specially engineered plants might be able to survive the harsh conditions and contribute to creating a breathable atmosphere. However, terraforming Mars is not just a technical challenge, it's an ethical one as well. If microbial life already exists on Mars, altering the planet's environment could destroy that life. This raises questions about our responsibility to preserve Mars in its natural state, and what rights, if any, alien organisms have. Another concern is the timescale. Terraforming Mars would likely take centuries, if not millennia, to achieve significant results. This means that any efforts we begin now would benefit future generations rather than ourselves. It raises the question of whether humanity is willing to commit to such a long-term project. Some scientists propose that instead of fully terraforming Mars, we should focus on building self-sustaining habitats within domes or underground. These controlled environments could provide Earth-like conditions without needing to transform the entire planet. This approach might be more feasible in the short term, while still allowing for human colonization. There are also geopolitical considerations. If terraforming becomes a reality, who will govern Mars? International agreements like the Outer Space Treaty state that no country can claim sovereignty over another celestial body. But the process of transforming a planet raises complex questions about ownership, control, and the rights of future Martian settlers. The potential benefits of terraforming Mars extend beyond colonization. Successfully transforming a planet could provide valuable insights into climate science and the ways we might address environmental issues on Earth. It could also be a test case for terraforming other planets or moons in the distant future. Mars's potential for terraforming fuels our hopes for becoming a multiplanetary species. While the challenges are immense, the dream of turning the red planet into a second home for humanity continues to inspire scientists, engineers, and visionaries alike. If we succeed, Mars could be the first step in humanity's expansion beyond Earth. Terraforming distant exoplanets is an even more ambitious goal than transforming Mars. With thousands of exoplanets already discovered, some of them potentially within the habitable zone, the idea of reshaping these worlds for human habitation captures the imagination. However, the challenges are exponentially greater than those we face with Mars. The first step in terraforming an exoplanet would be to assess its potential for supporting life. A planet within the habitable zone has the right conditions for liquid water, but other factors, like atmosphere, gravity, and temperature, must also be considered. Without these basic elements, any terraforming effort would be far more complicated. Distance is one of the greatest obstacles. Exoplanets are light years away, making travel and communication difficult. Any attempt to terraform these planets would require autonomous systems capable of functioning for decades or centuries without human intervention. Developing such systems would be a major technological breakthrough. Energy is another critical factor. The amount of energy required to change the atmosphere, climate, or surface of an exoplanet is immense. We would need to harness advanced energy sources, like nuclear fusion, or perhaps tap into the planet's own resources to drive the transformation process. A key challenge is creating or thickening an atmosphere. Many exoplanets may have atmospheres that are too thin or toxic for human life. We would need to release gases, much like the process proposed for Mars, to increase pressure, create warmth, and establish a breathable atmosphere. This process could take hundreds of years. Unlike Mars, where we have some understanding of the planet's conditions, distant exoplanets remain largely unknown. We can't yet measure their surface conditions in detail, and we don't know how their climates or ecosystems might respond to large-scale changes. This uncertainty adds a layer of complexity to any terraforming plan. Water is another essential element. We don't know if many exoplanets have significant water reserves, either frozen or underground. If a planet lacks water, we would need to find a way to deliver it from other sources, perhaps by redirecting ice-rich asteroids. This logistical challenge is unlike anything we've faced before. Terraforming exoplanets may require us to engineer entirely new ecosystems. On Earth, ecosystems are interconnected, with plants, animals, and microbes all playing vital roles. Recreating this complexity on another world would require an unprecedented level of scientific knowledge and technological control. There's also the question of how long it would take for terraforming efforts to succeed. Transforming an exoplanet could take thousands of years, far beyond a single human lifetime. The long-term nature of the project means that any benefits would be realized by future generations, raising questions about investment and commitment. Ethical considerations apply here too. If life already exists on an exoplanet, terraforming could have devastating consequences. The discovery of even microbial life could halt efforts, as we grapple with the moral implications of altering or destroying an alien ecosystem. The scale of terraforming distant exoplanets would also require unprecedented international cooperation. No single country or organization could undertake such a massive project on its own. It would require global collaboration, shared resources, and careful planning to avoid conflicts over ownership and control. Despite these challenges, the potential for terraforming distant exoplanets remains a powerful vision of humanity's future. It offers the possibility of expanding beyond our solar system, creating new homes among the stars, and securing the long-term survival of our species. While the journey will be long and difficult, the dream of reshaping distant worlds continues to drive scientific exploration. Ultimately, terraforming distant exoplanets pushes the boundaries of what we believe is possible. If we can overcome the immense technical, ethical, and logistical challenges, these planets could become the stepping stones to a future where humanity thrives across the galaxy. Creating Earth-like conditions on another planet or moon is an enormous challenge, requiring the transformation of nearly every aspect of the environment. One of the biggest hurdles is replicating Earth's atmosphere, which is finely balanced to support life. Achieving the right mix of nitrogen, oxygen, and trace gases is critical, but it's far from simple. On many planets, the atmosphere may be too thin or composed of gases that are toxic to humans. Transforming these atmospheres would involve releasing vast amounts of gases, potentially through industrial-scale processes. The challenge is not just introducing the right gases, but maintaining a stable atmosphere over time. Temperature control is another major concern. Earth's average temperature allows for liquid water to exist, which is essential for life. However, many planets are either too cold or too hot. Regulating planetary temperatures, perhaps by triggering greenhouse effects or building reflective structures to block sunlight, would be necessary to stabilize the climate. Gravity also plays a critical role. Many planets and moons have weaker gravity than Earth, which could affect human health over the long term. Prolonged exposure to low gravity can lead to muscle atrophy and bone density loss, which means we may need to artificially increase gravity, a challenge for which there is no current solution. Water availability is crucial for creating Earth-like conditions. While some planets might have ice reserves, many may lack liquid water altogether. Transporting water to these worlds or extracting it from underground sources presents enormous logistical and energy challenges. Another issue is radiation. Without a magnetic field like Earth's, many planets are exposed to harmful cosmic and solar radiation. Creating artificial magnetic fields or building habitats underground to shield humans from radiation would be essential for long-term survival. The composition of soil or lack thereof is also a significant challenge. Earth's soil is rich with nutrients that support plant life, but other planets may have barren or toxic surfaces. Modifying the surface of a planet to grow crops or sustain vegetation would require either importing vast quantities of material or developing ways to enrich the soil using local resources. Energy production is another key factor in creating Earth-like conditions. Any planet we attempt to terraform will need a reliable and sustainable source of energy, whether from solar power, nuclear reactors, or something else. Balancing energy needs with environmental stability adds another layer of complexity to terraforming efforts. Introducing an Earth-like ecosystem is also a challenge. Earth's ecosystems are complex, interdependent networks of organisms. Simply transplanting plants or animals to another world might not be enough. They would need to be carefully balanced with the new environment to avoid collapse or unintended consequences. Even if we could recreate Earth-like conditions, maintaining them is another matter. Planetary environments are dynamic, and without constant maintenance, they could revert to their original states. We would need advanced systems capable of monitoring and adjusting the atmosphere, temperature, and ecosystem over centuries. Ethically, creating Earth-like conditions raises questions about our responsibility to alien environments. Should we alter entire planets for human use, especially if there's a chance life already exists there? The decision to terraform must be weighed against the potential impact on the planet's natural state and any life it might harbor. Ultimately, creating Earth-like conditions on another world would require a combination of advanced technology, global cooperation, and a long-term vision. While the challenges are immense, the dream of transforming other planets to resemble our own continues to inspire those who envision humanity's future beyond Earth. Altering other worlds brings with it a range of ethical issues that we must confront before taking such monumental steps. One of the primary concerns is whether we have the right to change another planet's environment for our benefit. Transforming an entire world could potentially erase any unique features or natural history that planet holds. If life already exists on a planet, even in microbial form, altering that world raises the question of whether we are disturbing an alien ecosystem. Destroying or interfering with native life to make a planet more suitable for humans could be seen as a form of environmental colonialism, imposing our needs over what already exists. There's also the issue of responsibility. If we terraform a planet and later abandon the project, or if it fails, we could leave behind a damaged or unstable environment. The long-term consequences of altering an entire planet may not be fully understood, and we risk causing harm that could take centuries or longer to reverse. Ownership is another ethical dilemma. Who gets to decide how a planet is altered and for what purpose? Should entire planets be claimed by nations, corporations, or individuals? Or do these worlds belong to all of humanity, or perhaps to no one at all? The legal and moral frameworks for managing other planets remain unresolved. If terraforming efforts succeed, the next question is how we manage the resources of these altered worlds. Would the benefits of terraforming be shared equally, or would they only be accessible to the wealthiest nations or private companies? This raises concerns about inequality and the potential for space colonization to mirror the injustices seen on Earth. Cultural implications are also significant. If we find life on another world, even if it's not intelligent, what obligation do we have to preserve it? There is a profound ethical question about whether we should prioritize human expansion over protecting alien life forms that might have intrinsic value. Intergenerational ethics come into play as well. Terraforming a planet is a long-term project that would likely take centuries to complete. Do we have the right to initiate a process that will impact future generations, potentially binding them to live on worlds we've altered without their consent? The impact on Earth's environment must also be considered. Terraforming another planet could require vast amounts of energy and resources that might better be used to solve problems here at home. Before we commit to altering other worlds, we must ask whether those efforts could come at the cost of addressing urgent issues like climate change or environmental degradation on Earth. Another ethical issue is the potential for militarization. If nations or corporations compete over the resources or strategic value of a terraformed planet, it could lead to conflict. The militarization of space in the context of planetary alteration could have devastating consequences both in space and on Earth. Altering other worlds also invites questions about unintended consequences. Even with the best planning, we cannot fully predict how complex systems will react to large-scale changes. Altering a planet's atmosphere or biosphere could lead to unforeseen problems, such as runaway climate effects or ecosystem collapse. There's also the question of whether humanity is ready for the responsibility of altering entire planets. The environmental challenges we face on Earth suggest that we have yet to fully master the management of our own planet. Should we first demonstrate the ability to maintain and protect Earth's ecosystems before attempting to terraform another world? Ultimately, the ethical issues of altering other worlds revolve around the question of what kind of spacefaring species we want to be. As we expand into the cosmos, our decisions will reflect not just our technological capabilities, but our values and principles as a civilization. The choices we make will define our legacy in the universe. The long-term impacts of terraforming on humanity could be profound, shaping not just our future but how we view ourselves as a species. Transforming another planet into a habitable environment would mark a new era in human history, one where we no longer depend solely on Earth for survival. It would signify a shift from being an earthbound species to a multi-planetary civilization. Terraforming would fundamentally change our relationship with the natural world. On Earth, we are part of ecosystems that evolved over millions of years. But on a terraformed planet, we would be the architects of the environment. This new role could alter how we think about nature and our responsibility as stewards of life. The creation of new worlds would likely spark a wave of exploration and colonization, leading to the establishment of human settlements across the solar system. These new societies would develop their own cultures, shaped by the unique conditions of their planets. Over time, the diversity of human experiences could expand in ways we can barely imagine. Social and political systems would also be affected. Terraforming would require unprecedented levels of cooperation between nations, corporations, and possibly even new governing bodies dedicated to managing interplanetary resources. How we distribute the benefits of these new worlds could redefine global power dynamics and economic systems. Psychologically, living on a terraformed world would change how we perceive space and time. The vast distances between planets and the slower pace of terraforming could foster a different sense of patience and long-term thinking in human cultures. The mindset required for building and maintaining these new environments would likely emphasize sustainability and foresight. Terraforming might also spark a philosophical shift. As we become creators of new environments, questions about what it means to play God or reshape entire ecosystems could become central debates. Our view of life, evolution, and even our spiritual beliefs might evolve alongside our growing influence over other planets. One potential risk is the rise of a new form of inequality. If access to terraformed planets is limited to certain groups, it could deepen divisions within humanity. Those living on newly terraformed worlds might have advantages over those who remain on Earth, leading to complex issues of fairness and equity in the distribution of resources and opportunities. The environmental impacts of terraforming on humanity's mindset are also worth considering. As we master the ability to change entire planets, there is a risk that we might become less concerned about the environment on Earth. The belief that we can always terraform another planet could diminish our commitment to preserving the natural world we inherited. Over time, the physiological impacts on humans living on terraformed planets could also come into play. Adapting to different gravities, atmospheres, and ecosystems might lead to evolutionary changes, potentially resulting in future generations that are biologically distinct from those who remain on Earth. Culturally, the stories we tell about ourselves could shift dramatically. Myths, literature, and history will reflect humanity's ability to shape planets, transforming our collective identity from a species that evolved within a single ecosystem to one that can actively create new worlds. This could redefine what it means to be human. Technologically, terraforming would accelerate advances in fields like energy, biology, and environmental science. The skills and knowledge gained from transforming other planets could feed back into Earth-based projects, helping us solve problems such as climate change or resource depletion here at home. In the long term, terraforming could inspire humanity to think even bigger. As we learn to alter planets, we may begin to consider other large-scale projects, like harnessing the energy of entire stars or even reshaping galaxies. Terraforming could be the first step toward a future where humanity actively shapes the cosmos, extending our influence far beyond Earth. AI is revolutionizing spacecraft operations and navigation, making space exploration more efficient and autonomous. With the vast distances involved in deep space missions, real-time control from Earth is often impossible due to communication delays. AI systems can operate independently, allowing spacecraft to make decisions without waiting for instructions. In navigation, AI plays a key role in adjusting spacecraft trajectories. By processing vast amounts of data in real time, AI can predict obstacles, calculate the most efficient paths, and make course corrections instantly. This is particularly useful in avoiding space debris and ensuring the spacecraft stays on track. Autonomous navigation is crucial for missions to distant planets or asteroids. AI can analyze the gravitational fields of nearby objects and fine-tune a spacecraft's route, minimizing fuel consumption and maximizing efficiency. As missions move further from Earth, this capability becomes indispensable. AI also enhances spacecraft diagnostics and repairs. By continuously monitoring systems, AI can detect malfunctions before they become serious. If something goes wrong, the system can troubleshoot the issue and, in some cases, execute repairs or reroute power, ensuring the mission continues without interruption. Communication is another area where AI shines. Spacecraft far from Earth must deal with long communication delays. AI can act as an intermediary, managing signals and prioritizing critical information to send back, while handling routine tasks independently, reducing the burden on mission control. AI's ability to handle massive amounts of data is particularly valuable for scientific research. Spacecraft exploring planets, moons, or deep space environments collect vast quantities of information. AI helps process this data on board, identifying key patterns or anomalies that might indicate new discoveries. In space stations, AI can manage complex life support systems. By monitoring oxygen levels, temperature, and other environmental factors, AI ensures that conditions remain stable for astronauts. It can also predict when supplies will run low and optimize resource usage for long-term missions. Robotic exploration has also benefited from AI advancements. Rovers on Mars, for example, use AI to navigate rough terrain, select interesting rock formations to study, and even manage their own energy usage. This allows for more extensive exploration without constant guidance from Earth. Future spacecraft may rely even more heavily on AI for interstellar missions. With distances too great for humans to manage directly, AI will need to be fully autonomous, capable of conducting the mission, making real-time decisions, and adjusting to the unknowns of space. AI also offers potential in crewed missions, assisting astronauts with complex tasks and decision-making. Whether it's running simulations, analyzing spacecraft performance, or suggesting solutions during critical moments, AI could serve as an essential co-pilot on long-duration missions. However, integrating AI into space exploration does come with challenges. The systems need to be highly reliable and resilient, able to operate in extreme environments where hardware failures are common. Ensuring AI can adapt and learn from unforeseen situations is key to its future role in space. As AI continues to evolve, its role in spacecraft operations and navigation will only expand. It promises to make space exploration more autonomous, more efficient, and ultimately more capable of pushing the boundaries of what humanity can achieve in the cosmos. Robotics and automation are becoming indispensable tools in space travel, allowing missions to reach farther and perform tasks that would be impossible for humans alone. In environments that are too harsh or remote for astronauts, robots can act as explorers, carrying out complex operations with precision. One of the key roles of robotics in space travel is exploration. Robotic rovers, such as those on Mars, can navigate treacherous landscapes, collect samples, and analyze soil composition. These machines are equipped with tools to study planetary geology, search for signs of life, and prepare for future human missions. Automation also plays a crucial part in managing spacecraft systems. Autonomous systems can monitor and adjust spacecraft functions, from navigation to life support. This reduces the need for human intervention, particularly during long missions where communication delays make real-time control impractical. In orbit, robotic arms have become essential for tasks like repairing satellites, constructing space stations, and deploying scientific instruments. The Canadarm on the International Space Station is a prime example of how robotics can assist astronauts with heavy lifting and precise assembly in the zero-gravity environment. The future of space exploration will rely heavily on robotic systems for deep space missions. Sending robots to scout locations on moons, asteroids, and distant planets will help identify the best places for landing, mining resources, or building habitats. These missions will serve as precursors to human exploration. Robots are also being developed to assist astronauts during spacewalks. These robotic assistants could handle routine tasks or perform dangerous repairs outside a spacecraft, reducing the risks astronauts face when venturing into space. Their ability to work continuously without the limitations of fatigue is a major advantage. In space habitats, automation is key to managing daily operations. Robots can handle routine maintenance, monitor environmental conditions, and even manage agriculture in space farms. This allows astronauts to focus on more critical tasks, such as scientific research or mission planning. One exciting development in space robotics is the concept of autonomous mining. Robots could be used to mine resources on the Moon, Mars, or asteroids, extracting water, metals, and other materials needed for space construction or fuel production. This would reduce reliance on resupply missions from Earth. Robots designed for assembly and construction are also being tested for space applications. These machines could build habitats, research stations, or solar farms on distant worlds, laying the groundwork for human colonization. They could work in tandem with AI systems to adapt to changing conditions and solve problems on the spot. Robotics also has the potential to support medical care during space missions. Robotic surgery systems could be used in emergencies, allowing for remote medical procedures when astronauts are far from Earth. This technology could save lives during long-duration missions where immediate help is not available. The combination of robotics and automation is revolutionizing the way we think about space travel. As technology continues to advance, robots will take on more complex roles, enabling humans to explore deeper into the cosmos while relying on these machines for support, safety, and efficiency. In the long run, robotics and automation may become our primary tools for establishing a sustainable presence in space. They will allow us to push beyond current limitations, laying the foundation for permanent settlements on other worlds and turning science fiction into reality. Autonomous spacecraft maintenance is revolutionizing how we approach long-duration space missions. As missions venture farther from Earth, the ability to perform repairs and upkeep without human intervention becomes increasingly crucial. This autonomy allows spacecraft to remain operational, even in the most remote regions of space. AI systems are central to autonomous maintenance. These intelligent systems can monitor spacecraft components in real time, detecting wear and tear before it leads to critical failures. By analyzing data collected from sensors, AI can identify anomalies and predict when maintenance is required. One of the key advantages of autonomous maintenance is the reduction of downtime. When a spacecraft can self-diagnose and perform repairs, it minimizes the need to wait for instructions or support from mission control. This capability is particularly important during deep space missions, where communication delays can be significant. Robotic systems can assist in the physical maintenance of spacecraft. Equipped with specialized tools, these robots can perform tasks such as replacing parts, tightening bolts, or conducting system checks. Their ability to work in harsh environments without human presence is a major asset in maintaining spacecraft integrity. In addition to routine maintenance, autonomous systems can handle emergency repairs. If a critical system fails, the spacecraft can initiate protocols to address the issue. This quick response capability is essential for ensuring crew safety and mission success in environments where help is far away. The integration of advanced machine learning algorithms enhances autonomous maintenance. These systems can learn from previous repairs and adjust their strategies based on outcomes. Over time, they become more efficient and effective at diagnosing and addressing issues, significantly improving reliability. Moreover, the ability to perform autonomous maintenance can extend the lifespan of spacecraft. By continuously monitoring and repairing systems, spacecraft can operate far beyond their originally planned mission durations. This longevity could allow for more extensive exploration of distant planets and moons. Safety is a primary concern in spacecraft operations, and autonomous maintenance can enhance safety protocols. By reducing human involvement in potentially hazardous tasks, the risk to astronauts is minimized. Autonomous systems can handle dangerous repairs, such as those involving high-voltage equipment or exposure to radiation. The data collected during autonomous maintenance can also contribute to future mission planning. By analyzing patterns and outcomes, engineers can improve designs and maintenance procedures for subsequent missions. This feedback loop enhances our understanding of how spacecraft perform over time and under different conditions. As technology progresses, the potential for fully autonomous spacecraft maintenance will only grow. Future missions may rely entirely on these systems to ensure that every component is functioning optimally. This shift will enable humans to focus on scientific research and exploration while the spacecraft takes care of itself. The concept of autonomous maintenance aligns with the broader trend of automation in space exploration. As we develop smarter and more capable systems, the role of human operators will shift, allowing for more efficient missions. This evolution marks a new chapter in our journey beyond Earth, where machines and humans work together seamlessly. Ultimately, autonomous spacecraft maintenance is essential for the future of deep space exploration. By ensuring that spacecraft can operate independently and effectively, we pave the way for humanity to push the boundaries of what is possible in our quest to explore the universe. The future of AI crewed space missions holds immense potential for revolutionizing how we explore the cosmos. By integrating artificial intelligence into crewed spacecraft, we can enhance efficiency, safety, and decision-making processes. As missions become longer and more complex, AI will play an increasingly vital role in supporting human astronauts. AI can assist in managing spacecraft systems, from life support to navigation. By monitoring critical parameters and making real-time adjustments, AI can help maintain optimal living conditions for crew members. This capability reduces the cognitive load on astronauts, allowing them to focus on scientific research and exploration. One of the most promising aspects of AI in space missions is its ability to analyze vast amounts of data quickly. During exploration, AI systems can sift through data collected from instruments, identifying patterns and anomalies that require further investigation. This speed and accuracy can lead to more timely discoveries and insights about the environments we are studying. Autonomous decision-making capabilities will empower AI to act swiftly in emergencies. If a critical system fails or a hazardous situation arises, AI can evaluate the situation and implement solutions without waiting for human input. This quick response could be crucial for the safety of astronauts in the unpredictable environment of space. AI can also enhance communication during missions. By streamlining data transmission and processing information, AI can ensure that crew members have access to critical updates and resources, even when communication with Earth is limited. This capability helps maintain a clear line of communication and supports effective teamwork. The psychological well-being of astronauts is another area where AI can make a difference. AI systems can monitor crew members' health and emotional states, providing insights and suggesting interventions when needed. By recognizing signs of stress or fatigue, AI can help maintain the mental health of astronauts during long missions. Incorporating AI into crewed missions opens the door to more complex and ambitious projects. With AI handling many of the operational tasks, astronauts can engage in deeper scientific inquiries and exploration. This partnership allows for a more focused approach to research and discovery. Future AI systems will likely be designed to learn and adapt based on experiences. By analyzing outcomes from previous missions, AI can improve its performance and decision-making capabilities. This continuous evolution will enhance the effectiveness of AI as a co-pilot in space. AI's role in space missions will also extend to habitat management. As humans establish bases on the Moon, Mars, or other celestial bodies, AI will help regulate life support systems, resource management, and even agriculture. These systems will be essential for sustaining human life in off-Earth environments. The ethical implications of AI in space exploration must be considered as well. As we entrust AI with more responsibilities, we need to establish guidelines for its use and ensure that human oversight remains a priority. Balancing the benefits of AI with ethical considerations will be crucial for the future of space exploration. Education and training will evolve alongside advancements in AI technology. Astronauts will need to learn how to work effectively with AI systems, understanding their capabilities and limitations. This new paradigm will require a shift in astronaut training programs, focusing on collaboration with intelligent machines. Ultimately, the future of AI crewed space missions promises to redefine our capabilities in exploring the universe. By leveraging the strengths of AI alongside human intuition and creativity, we can push the boundaries of what is possible in our quest to understand the cosmos and our place within it. Current space treaties and agreements play a vital role in governing activities beyond Earth. The Outer Space Treaty, established in 1967, serves as the cornerstone of international space law. It outlines that space exploration should be conducted for the benefit of all humanity and prohibits the placement of nuclear weapons in space. Another significant treaty is the Rescue Agreement, which emphasizes the obligation of countries to assist astronauts in distress, regardless of their nationality. This principle of mutual aid underscores the shared responsibility of nations to ensure the safety of those exploring outer space. The Liability Convention addresses the issue of liability for damage caused by space objects. If a spacecraft from one country causes harm to another nation's property or personnel, this treaty ensures that the offending country is held accountable. This framework is essential for maintaining peace and cooperation in space activities. The Registration Convention requires that states provide information about their space objects to the United Nations. This transparency is crucial for tracking and identifying objects in orbit, reducing the risk of collisions and enhancing safety in space operations. It also fosters a spirit of cooperation among nations. In recent years, the increasing involvement of private companies in space activities has prompted discussions about how existing treaties apply to commercial enterprises. Many of these treaties were designed with government entities in mind, leading to questions about their adequacy in regulating private space exploration. The Moon Agreement, adopted in 1979, aims to establish a framework for the exploration and use of the Moon and other celestial bodies. It emphasizes that these environments are the common heritage of mankind and should not be claimed by any single nation. However, the Moon Agreement has not been widely adopted, limiting its effectiveness. As space exploration advances, new agreements are being proposed to address emerging challenges. For instance, discussions about space debris management and the sustainability of space activities are gaining momentum. Collaborative efforts to mitigate space debris will be crucial to ensuring the long-term viability of orbits around Earth. The increasing militarization of space has also raised concerns among nations. The lack of binding agreements on the military use of outer space is prompting calls for new treaties to prevent conflicts. Ensuring that space remains a peaceful domain will require ongoing diplomatic efforts and dialogue. Moreover, the issue of resource exploitation is becoming more pressing. As private companies eye the potential for mining asteroids or the Moon, questions about ownership and rights to these resources arise. The existing treaties do not provide clear guidelines for such activities, necessitating the development of new frameworks. International cooperation is essential for addressing these evolving challenges. Nations must work together to establish agreements that balance national interests with the collective needs of humanity. Collaborative projects, like the International Space Station, demonstrate the potential for nations to unite for common goals in space. As we look to the future of space exploration, the development of new treaties and agreements will be crucial. The international community must adapt to changing technologies and the increasing participation of private entities. Building a comprehensive legal framework for space activities will help ensure that exploration is conducted responsibly and sustainably. Ultimately, the landscape of space treaties and agreements will continue to evolve as we push further into the cosmos. Balancing national interests with global responsibilities will be key to maintaining peace and cooperation in the final frontier. As humanity reaches for the stars, the importance of these agreements cannot be overstated. The role of nations in deep space exploration is critical as humanity expands its reach beyond Earth. Each nation brings its own resources, technologies, and expertise to the table, fostering international collaboration. This collective effort is essential for tackling the numerous challenges associated with exploring the cosmos. Governments have historically led the charge in space exploration, establishing space agencies to develop and execute missions. Organizations like NASA, ESA, and Roscosmos have paved the way for scientific discoveries and technological advancements. Their initiatives not only explore distant worlds, but also inspire future generations to pursue careers in science and engineering. International cooperation has become increasingly important as missions grow more ambitious. The International Space Station serves as a prime example of nations working together to achieve common goals in space. This collaboration has proven that shared expertise can lead to significant advancements in research and technology. National interests often shape the direction of space exploration. Countries invest in missions that align with their strategic objectives, such as enhancing their technological capabilities or asserting their presence in the global arena. This competitive aspect can drive innovation, but may also lead to conflicts over resources and territory in space. Emerging nations are beginning to make their mark in space exploration, contributing to the global effort. Countries like India and the United Arab Emirates have successfully launched missions to the Moon and Mars, demonstrating that space exploration is no longer the domain of just a few powerful nations. These developments encourage diversity in perspectives and approaches to exploration. The role of private companies in space exploration is also reshaping the landscape. Governments are increasingly partnering with commercial entities to leverage their capabilities and drive down costs. This collaboration allows nations to focus on scientific goals, while private companies handle the logistics and technology needed for missions. National security considerations often play a role in shaping space policies. As the potential for conflict in space grows, nations are keen to develop technologies that protect their interests. This drive for security may lead to increased militarization of space, which poses ethical and diplomatic challenges for global cooperation. Research and development funded by governments are crucial for pushing the boundaries of space exploration. Investments in technology can lead to breakthroughs that benefit not just space missions but also life on Earth. Innovations developed for space applications, such as satellite technology, often have significant terrestrial benefits. Education and public outreach are important aspects of a nation's role in space exploration. By engaging citizens in the excitement of space, countries can foster a culture of curiosity and innovation. This engagement is essential for generating public support for funding and future missions. The involvement of nations in deep space exploration also raises questions about governance and policy making. As exploration efforts expand, it becomes essential to establish clear guidelines for behavior in space. Nations will need to collaborate to create frameworks that prevent conflicts and ensure responsible exploration. Scientific collaboration across borders can lead to groundbreaking discoveries. Sharing data, resources, and expertise enhances the overall success of missions. Joint missions, such as those between NASA and ESA, exemplify how pooling knowledge can lead to more profound insights about the universe. As humanity ventures further into deep space, the role of nations will continue to evolve. The challenges of exploring other worlds require cooperation, innovation, and a commitment to shared values. Navigating these complexities will be key to ensuring a sustainable and peaceful future in space exploration. The potential for space wars and territorial claims is a pressing concern as humanity ventures further into the cosmos. With more nations and private companies entering space, the competition for resources and strategic advantages is likely to intensify. This race could lead to conflicts over territories and celestial resources, mirroring historical rivalries on Earth. Currently, international treaties, such as the Outer Space Treaty, prohibit nations from claiming sovereignty over celestial bodies. However, as exploration and commercialization of space grow, these agreements may not be sufficient to prevent disputes. Nations might seek to establish claims over resources like water, minerals, or potential habitats. The Moon and asteroids are particularly attractive targets for resource extraction. These bodies contain valuable materials that could support life on Earth or be used in future space missions. The desire to tap into these resources may provoke territorial disputes, raising questions about ownership and rights in space. The involvement of private companies adds another layer of complexity. Corporations may pursue mining rights or land claims, which could conflict with national interests. The lack of clear regulations governing commercial activities in space creates an environment ripe for disputes and competition. Technological advancements in space capabilities further heighten the potential for conflict. As nations develop their military space programs, the likelihood of militarization increases. This could lead to a scenario where space is viewed as a new battleground, with nations seeking to establish dominance over strategic locations. There is also the risk of accidents or miscommunications escalating into conflict. With multiple entities operating in close proximity in space, misunderstandings can occur, leading to unintended confrontations. Establishing protocols for communication and conflict resolution will be essential to mitigate these risks. The concept of space debris complicates the situation as well. As more spacecraft and satellites are launched, the likelihood of collisions increases. If a collision were to cause significant damage, it could trigger disputes over accountability and compensation among nations and companies involved. National security concerns will likely drive governments to invest heavily in space defense systems. This could lead to an arms race in space technologies as nations seek to protect their assets and maintain strategic advantages. The resulting military buildup may further escalate tensions in an already competitive environment. Cooperative frameworks could provide a pathway to preventing space-related conflicts. Establishing international agreements that govern activities in space and outline shared responsibilities could promote peaceful coexistence. Such collaborations would be crucial in fostering dialogue and reducing the potential for territorial disputes. The ethical implications of space territoriality are significant. As we extend our reach into the cosmos, we must consider the moral responsibility of altering other worlds. The potential for conflict over resources raises questions about our stewardship of the universe and our obligation to protect the natural state of celestial bodies. Educational outreach and public discourse about space governance are essential for shaping future policies. Engaging the global community in discussions about territorial claims and resource management can lead to more informed decisions. Building a shared understanding of the challenges ahead will be crucial for ensuring that space remains a domain of peaceful exploration. Ultimately, the potential for space wars and territorial claims underscores the importance of establishing clear rules and norms for behavior in space. As humanity reaches for the stars, our ability to navigate these complexities will determine whether we can coexist peacefully in the final frontier. The influence of private companies in space exploration has grown significantly over the past few decades. Companies like SpaceX, Blue Origin, and others have entered the field with ambitious goals, transforming the landscape of space travel. Their involvement has accelerated technological advancements and driven down costs, making space more accessible than ever. SpaceX in particular has made headlines with its innovative approaches to rocket design and reuse. The Falcon 9 rocket, known for its ability to land and be reused multiple times, has drastically reduced the cost of launching payloads into space. This reusability model sets a new standard for efficiency in the aerospace industry. In addition to cost savings, private companies are pushing the boundaries of what is possible in space. SpaceX's Starship program aims to facilitate missions to the Moon, Mars, and beyond, with the ultimate goal of enabling human colonization. Their ambitious vision encourages other companies to innovate and explore new frontiers. Collaboration between governmental space agencies and private companies has become increasingly common. NASA's partnerships with companies like SpaceX and Boeing have allowed for the development of the Commercial Crew Program, which transports astronauts to and from the International Space Station. This synergy leverages the strengths of both public and private sectors. Private companies are also expanding the range of missions and services available. Beyond launching satellites, they are exploring areas such as space tourism, asteroid mining, and lunar exploration. This diversification opens new opportunities for research, investment, and economic growth within the space industry. The rise of private companies raises questions about regulation and governance in space. With multiple entities operating in orbit and beyond, ensuring compliance with international treaties becomes more complex. Establishing clear guidelines for commercial activities will be essential to prevent conflicts and protect shared resources. Public interest in space has been reignited by the activities of private companies. High-profile missions and ambitious plans capture the public's imagination and inspire a new generation of explorers and scientists. This renewed enthusiasm is vital for securing funding and support for future space endeavors. Private companies are also contributing to the democratization of space. As launch costs decrease, more countries and organizations can access space. This expanded participation encourages a broader range of scientific research and cultural contributions from diverse voices around the globe. The technological innovations developed by private companies often have significant terrestrial applications. Advances in materials science, robotics, and data analysis used in space exploration can benefit other industries. This cross-pollination of ideas fosters overall technological growth and enhances capabilities on Earth. The influence of private companies can also lead to competition, which may drive progress but can introduce challenges. Rivalries between companies can create pressure to prioritize speed and profit over safety and ethical considerations. Striking a balance between competition and responsibility will be crucial as the industry evolves. Moreover, the emergence of private space companies emphasizes the importance of public engagement and accountability. As these entities gain more influence in space exploration, their actions and decisions must reflect the values and interests of society. Transparency and community involvement will be essential in shaping the future of space endeavors. Ultimately, the rise of private companies like SpaceX marks a new era in space exploration. Their contributions are reshaping our approach to the cosmos, enabling us to reach new heights and explore the unknown. The influence of these companies will continue to define the future of space travel and exploration in ways we are just beginning to understand. Global collaboration is essential for advancing our efforts in deep space exploration. As we push the boundaries of what is possible, no single nation can bear the enormous costs and challenges associated with these missions alone. Collaborative initiatives can pool resources, expertise, and technology from around the world, maximizing our potential for discovery. Joint missions between countries can facilitate scientific research that benefits everyone involved. For instance, projects like the International Space Station demonstrate how countries can work together to conduct experiments and share knowledge. This collaborative spirit fosters camaraderie and creates a sense of shared purpose in our exploration of the cosmos. The establishment of international partnerships can also enhance technological development. By sharing research and innovations, nations can accelerate advancements in areas such as propulsion, life support systems, and robotics. This exchange of ideas can lead to breakthroughs that might not be possible through isolated efforts. Moreover, global collaboration can help address the ethical challenges of deep space exploration. As we consider the implications of colonizing other worlds and utilizing extraterrestrial resources, diverse perspectives from different cultures and countries will enrich the conversation. Inclusive dialogue can ensure that our actions reflect a shared commitment to responsible stewardship of the cosmos. International space treaties provide a framework for collaboration, outlining principles that govern activities beyond Earth. As more nations and private entities enter space, these treaties must evolve to accommodate new realities. Ensuring that agreements promote cooperation and prevent conflicts will be crucial for the future of deep space endeavors. The involvement of emerging space nations in collaborative efforts is also important. Countries that have recently developed space programs bring fresh perspectives and innovative approaches to exploration. By engaging these nations, the global community can create a more equitable landscape for space exploration. Education and outreach play a vital role in fostering global collaboration. By inspiring the next generation of scientists, engineers, and explorers worldwide, we can build a strong foundation for future missions. Programs that promote international cooperation in education can cultivate a sense of shared responsibility for our collective journey into deep space. Data sharing among countries is another key aspect of collaboration. Open access to scientific findings and resources can lead to faster advancements in our understanding of space. By making data available to researchers across the globe, we can accelerate progress and encourage new discoveries. Public engagement is essential for sustaining interest and support for deep space exploration. Collaborative missions often capture the public's imagination, fostering enthusiasm and investment in future endeavors. By involving citizens in discussions and education initiatives, we can create a more informed global community. Funding for deep space initiatives can benefit from international collaboration as well. Joint missions allow countries to share the financial burden of expensive projects, making ambitious goals more achievable. This shared investment can lead to more comprehensive and effective exploration strategies. The role of private companies in global collaboration is also significant. As commercial space entities become more involved, their partnerships with governmental agencies can expand the scope of exploration. Combining the agility of private companies with the resources of nations can lead to innovative solutions for deep space challenges. In conclusion, the future of deep space exploration hinges on our ability to work together as a global community. By fostering collaboration among nations, we can address the myriad challenges ahead and expand our understanding of the universe. Together, we have the potential to unlock the mysteries of deep space and make remarkable discoveries for all of humanity. As we've explored in this video, the future of space exploration is filled with exciting possibilities and significant challenges. From the advancements in AI and robotics to the ambitious goals of terraforming other planets, humanity stands on the brink of a new era in our quest to understand the universe. The integration of technology into space travel promises to enhance our capabilities, making deep space missions more efficient and sustainable. We discussed the potential impacts of private companies like SpaceX and Blue Origin, which are reshaping the landscape of space exploration. Their innovations and competitive spirit have driven costs down and expanded access to space, allowing more nations and organizations to participate in this monumental journey. This shift is creating a dynamic environment where collaboration and competition coexist, fostering a spirit of discovery. The ethical considerations surrounding space exploration were also highlighted, particularly regarding the impact on other worlds. As we look to alter environments for human habitation, we must weigh our responsibilities and the potential consequences of our actions. The discussions about territorial claims and the militarization of space remind us that as we explore new frontiers, we must do so with care and respect. International cooperation emerged as a crucial theme throughout our exploration. The existing treaties and agreements provide a framework for how nations can work together to navigate the complexities of space. Engaging emerging space nations and fostering collaboration in education and research are vital for building a shared vision for our future in space. The idea of autonomous spacecraft maintenance and AI-assisted problem-solving showcases how technology can empower us to tackle the challenges of deep space. These advancements not only enhance our operational capabilities, but also ensure the safety and well-being of astronauts venturing far from Earth. The future of AI in space missions holds immense promise for supporting human exploration. As we contemplate the potential for discovering extraterrestrial life, the implications of finding other civilizations weigh heavily on our minds. From philosophical debates to the responsibilities we would have, the discovery of life beyond Earth would undoubtedly change our perspective on our own existence. It is an exciting frontier that calls for careful consideration and open dialogue. We've also delved into the practicalities of resource management in space, discussing the challenges of accessing and utilizing materials from other planets and asteroids. This aspect of space exploration will be key to establishing sustainable colonies and making long-term human presence in space a reality. The innovative approaches we develop now will shape the future of humanity among the stars. As we wrap up this comprehensive look at the future of space exploration, we encourage you to reflect on the vast opportunities and responsibilities that lie ahead. The journey into deep space is just beginning, and every step we take brings us closer to understanding our universe and our place within it. If you enjoyed this video and found it informative, please give it a thumbs up and subscribe to our channel. Your support helps us continue to create engaging content about space exploration and technology. Don't forget to check out our other videos for more insights into the wonders of the cosmos and the exciting future of humanity in space. Thank you for watching.